red light. Okay, welcome everybody. Tonight is the 26th of January in 2021. My name is Carl Ott. I'm the current president of the Dallas Personal Robotics Group Robot Builders Club. And we're going to do our usual Tuesday night or Wednesday afternoon, depending on your time zone meeting, where we go around the table or the screen and talk about projects we're working on, projects we are want to work on next week. And, if we have stuck questions, we want to put them out to the group. There's a lot of good experience. And we love to just bring people in and help out when people get stuck. So with that, we'll just start going around the table. So think about if you want to jump in, guys. But for now, I think Chris from the Great Northeast has something to bring up.
All right. Thank you, Carl. So last weekend in the emails, I've picked the group's brain, if you remember, about my line following. I wouldn't say challenges, but again, the question of how to get a line on the floor without damaging the floor, and pick the line up with the QTR array here. So just showing that for the benefit of those who weren't on last week. So again, I just want to go down my hallway in a smooth fashion and repeatable fashion and collect some LiDAR data and other data. So the suggestions I got, in response to the challenge I brought up, which was, my wood floor is reflecting almost as much IR as kind of the tape. So there were two suggestions that I got from the group. One was to kind of create some shielding around the QTR individual sensors there, just create some shielding around it so that there's less crosstalk. The other suggestion was to effectively angle the sensors so that maybe I don't get as much of a reflection and extreme reflection from my shiny wood floor. So I tried those things. They didn't really help. It still was basically struggling a lot to distinguish, not so much distinguish between a white tape on the floor and the wood floor, but the wood floor would occasionally, give a reflection that's as much as the white tape. All the things I tried, they just kind of proportionally reduced the strength of the signal. But again, it was proportional. The floor just reflected less. The white line reflected less. I even tried to PWM the IR LEDs, to effectively put out less IR. Again, hoping that the wood floor would disproportionately reflect, back less. But everything was in the end just proportional. So the problem didn't go away. The wood floor is just still showing up as a white line occasionally. So in the end, I had to go low tech. All right, and let me just present one slide here. I had to go low tech to make it work, which is a bit annoying. So in the end, what I had to do is I printed some black lines on white paper, 2 lines per sheet of paper, printed a couple sheets of paper out, and then cut it in half and taped that paper down on the floor. And of course, that works perfectly because now I've got, very crisp black line on white background. It doesn't get any better than that. So that works. It's of course a lot more work than I was hoping to do. And again, I want to go around the corner here and another corner and into a room and back, right? So it's it's a bit more involved than I was hoping that to be. I was just hoping I could just put the tape down on the floor and be done. So this will work. And I think in the end I had to realize, what, I'm doing this because I want to collect some other kind of data. And so if I spend too much time on solving this problem, right, it's just kind of a distraction. So it's just, I figured, okay, I might as well put in a little bit extra time putting down this paper, it's low tech again, but it works. So I'll do it this way. I'll have to refine the method a little bit because there's some spots that are reflecting even though they're black. And at least that I can get to what I actually want to do, which is just follow the damn line and with the LiDAR spinning and collect some data. So all of this is really just the means to an end, and so I think all of us sometimes go down some rabbit hole. You're trying to solve a problem so you can get to the other problem that you want to solve, and you end up spending too much time on something. So I had to call it a day, and just do what I had to do to get some damn line on the floor. So that's where I'm at. It doesn't go much further than what's seen in the picture here, but I do want to go further down the hall and like I said, make a couple turns, and then traverse that line as smooth as possible with the LiDAR going, and collect some good LiDAR data and perhaps some other data, and then run that offline through algorithms, with different parameter settings, so I can find the best parameter setting for various algorithms. So that's the plan. That's where I'm at with that. So, any questions?
So is that
Sounds appropriate.
it looks pretty cool. Is it sitting flat, or did you actually have to tack it down to the floor somehow?
Well, that's the thing, right? That's what makes it a little more involved. I did have to tape down all the edges, right? Because otherwise, any foot traffic is immediately going to tear up the whole thing,
Yeah.
right? So that's what makes it time consuming, right? Compared to just having the right kind of tape, zip, putting the tape down. So, and then the transition from one sheet of paper to the next, there was a little white gap. I taped it over with white tape. I used a Sharpie to make that white tape black, but it turns out that's reflecting. That Sharpie on top of white tape does not show up as black. It shows up as white. All right, so it's like, again, one thing after the other. I got pretty annoyed with this. So it's but I'll be able to refine this approach a little bit, and then just call it a day and get my LiDAR going and collect data. So
I was having pretty good luck with black poster paint showing up as black on my styrofoam.
okay.
And how's the traction on that paper?
Well, so my wheels, my wheelbase, so I forgot what the exact numbers are, right? But the paper, it's like half a sheet of paper, so 8.5, that's 4.25 inches, right? So it's right in between here, right? So the wheels usually are not on the paper or on that pink tape. They're just outside it, or maybe on the pink tape. And I did have some traction issues now that you bring it up, and that was with the with the tubing attached to my QTR to kind of shield out any crosstalk, but that meant that tubing was almost touching the floor, right? And so any piece of paper that sticks up a little bit, you just get caught on it. And because I didn't have a lot of traction, the wheels were spinning occasionally. So that's why, again, I had to carefully, anywhere where there's a transition from paper to paper or paper to floor, I had to tape everything down. Otherwise, it might get caught, or the foot might get caught, right, and tear the whole thing up. So it's just not ideal, but it gets the job done.
Hey, Chris, I did have one suggestion, which came from my own experience, is that I don't know if anybody looked, but I had posted a YouTube video of watching my robot spin, and I had tried to do it on a wood floor, tried to do it on carpet. On carpet, it makes my robot kind of pirouette, but on particle board, it's a nice traction surface, but it's very, very smooth. And I thought about you when I was playing with that, and you can buy a 4x8 sheet of particle board for just about nothing. You could cut it into strips and build yourself something that could be put down on the floor.
The problem is the space I'm using is going to receive foot traffic by 2 kids, a wife, and sometimes a dog, right? And so I can't just do whatever the heck I want there.
Man in his castle.
Are you concerned about the stairwell?
I am. So far, none of my robots have fallen down that stairwell, but yeah, it is it is a concern.
I have one as well, and it's once it gets rolling, it's one of my concerns. So maybe with odometry, I can put a geofence there.
Yeah. So usually when I run it, I stay close to the keyboard, and I have a little e-stop function, so I can, if something gets out of control, I just pull the plug, so to speak.
Well, Pat, one of the things I've been doing is I built a whole bunch of pieces of wood that are like this, and I put them all over the place when I'm running on my deck so it can't come off the edge of the deck. So I just put barriers up.
Yeah, that might be what I do when I first start going autonomous, is to put a barrier at the edge of the stairs.
Oh, that spoils the fun. What happened to living on the edge?
Exactly. I do have a question for Ray, and it pertains to the Romy. So let me stop presenting, or anybody else who has the Romy platform. But I know, Ray, you have one, right? And here's the battery compartment. What I found is the batteries in there are a little loose. And when I bump into something, it's enough to cause an intermittent contact of the batteries and the contacts in there, and boom, I lose power for a split second, and everything reboots. I've added a pretty large electrolytic cap to compensate a little bit, but it's not enough because the Pi is sucking quite a bit of power. So Ray, I don't know if you have seen similar issues with your Romy platform. No? Yeah, it's really, I mean, I gotta do something about it, because anytime I bump into something, it's you can hear the batteries, they're just, I mean, it doesn't look like there's something wrong, but there is just not a lot of tension on these springs, right? And you bump into something.
Have you tried stretching the springs to make them a little more resilient?
I haven't tried that. Good idea. I tried inserting stuff to prevent the batteries from moving around, but I will try stretching the springs a little bit.
You could try putting a metal washer between the positive contact and the end.
That's sort of what I've done. Yes, it's sort of what I've tried, and yeah, it's still not happy, but it did improve things. So that's all.
I wonder how that black gaffer's tape would perform.
Black gaffer's tape on directly on the floor, or
yeah.
See, the issue is not the tape, right? I've previously done. I did this white tape on the floor, and I'm picking the white tape up perfectly, and there's enough contrast between the white tape and the floor most of the time. But the floor kind of, if this is the signal, I get a small signal, but occasionally I get a spike and another spike. So it's fluctuating quite a bit. You can see in the picture, you saw in the picture, the floor is a little bit reflective. It's dark, but occasionally it reflects almost as much as the white tape. So I was just getting a signal that's all over the place from the floor, right? So it's not the tape that's the issue. It's the floor that's the issue. And that's why I had to go with the solution of, I got to put something else on top of the floor and then another line on top of that.
If you have something that's very opaque and very absorbent, is that enough contrast?
And put that where? So again, it's I have the right tape. I can pick up the tape, but the moment I'm off the tape, the signal from the floor is all over the place unless I cover up the floor.
Well, that's the easy answer. You need to put the opaque IR, black, reflective, absorbent paint on your hardwood floor. Then it probably solved.
I don't think when I throw a gallon or two of that chalk paint, just all over your floor, you're done.
You're done.
Right.
Good idea.
Cement paint and black chalk paint, you're done.
Why did I
enjoy
think
it?
of that?
They go right on the floor all the time that way. Yeah.
The other
we always like to make things more complicated than necessary.
Buy one of those little Makita orbital sanders and put it in front of your sensor.
Okay, I got a couple good ideas. Let me write those down.
Chris is like, I appreciate all of this, I really do, but
I don't think that ice hockey or wherever that one where they they have the real people clinging out in front of the puck. Yes.
You know, if you're concerned about your significant other, bring her on. We'll convince her. It's no problem, really.
Yeah, we got you.
No, I mean, I kind of like my floors too. It's, so I do want to keep them. So,
all righty.
Anyway, I have a solution. It's a bit more work, but whatever.
Cool.
Thanks for all the ideas.
Yeah.
Yeah, congratulations. Gonna work you on.
All right. So let's see. So we have quite a group forming here now. Hanavia, are you guys ready, or should we stall a little longer and go around to someone else?
We're good to go.
Good to go?
Yep.
Okay, cool. Well, then we'll turn it over to you all. Just present and be sure to introduce yourselves. And this should be a good discussion. So
yeah,
have at it.
So I'm Jose, and I led most of the CAD. For this, what we're showing off is a ring shooter. So for FTC robotics, the challenge is to launch these rings into some goals. So of course we want to use a shooter to get that done, and that's what we're going to show off today.
Now we've got Cooper and Paul here. Say hi, guys. They are trying to assemble the actual physical version of it. We'll see how it goes. But go ahead, Jose.
And this is the Iron Rain team, right?
This is the high school team Iron Rain.
Very good.
I have a presentation.
Let's
see. Might not be able. Let's see. So can you guys see this?
Yeah.
Ring shooter?
Yeah. So this diagram will show basically all the parts it has. So on the center, we have a custom-made flywheel. You see it has the aluminum plates, and that center red part, that's made out of Ninja Flex. It also has some flaps on it, so it can get more points of contact on the ring, which you can see is this right here. It's made up of 3 plates and several walls. The center plate is where the ring rests on. That's where all its pathing will go through. The top plate keeps it from falling down. Well, escaping basically, escaping from the flywheel. And then we have a bottom plate that's serves for support for the center one, since it can be attached to the center. And then also on the right, we have a Rev ultraplanetary motor. It has a 3-to-1 ratio because we need to go as fast as possible to make sure that we can launch the ring as far as possible. And in order to get the ring into the flywheel, we have this, what we call the ring flipper, which is like what would you call this? Something like a stick. Just call it that, on a servo that'll rotate the ring into the flywheel. So, and this will show the process of how it came to be in CAD. The first, yeah.
Which CAD tool are you using, Jose?
We use Autodesk Fusion 360.
Nice.
Yeah, one of my favorites.
Yeah.
You guys know how to use it way better than I know how to use it. I'll tell you that.
How many years you been doing CAD, Jose?
I started freshman year, so I guess now I'm junior year, so that would be, well, maybe not like 2 complete years, more than 2.
Now we're lucky to have, I think, 4 people who do CAD, mostly in Fusion.
I can make a box and put a hole in it. That's about as good as I get with it.
So we're lucky enough to have a CNC machine, so all these aluminum parts we can just make.
Yeah, I was going to ask who made the thing, and you can say, well,
Yeah.
that's awesome.
Yeah. So you can see even this huge center plate here, we were able to make it, manufacture it ourselves.
How big is that?
The center plate, probably like 12, 14 inches wide. Haven't like checked the exact length, but it's pretty big.
They do everything in metric also, so he's translating to English units.
See, and we're even able to use it on the center we needed a custom pulley with this hole in the middle to accept some bearings. So just threw a cutter on the MDF board, got the pulley in there, and then we can just have the CNC cut out that hole for us. And we also have a 3D printer. So all of those sidewalls, we can just print. They do take quite a while though.
Which brand is the CNC?
It's Omeo something.
Yeah, it's a Chinese manufacturer, Omeo. I don't remember the model. I could go take a look.
That's pretty good size.
Yeah, this one is about. I think you can do 24 by 48 almost. Well, maybe 34. That's 36. Where's the brand? It's X8-2200.
So when you cut out the metal, do you have it air cool, or do you have all, or how do you keep the bit?
Not that sophisticated. There's a person standing there putting oil on it.
Ah, okay.
And yes, just air cool. There is a mist system, but we haven't set it up yet.
Because yeah, when you cut metal, you have to take care of the heat problem.
Not so much for aluminum, I don't think.
Not as much, but even it can have issues with the bit.
It is better to cool it because the aluminum can get gummy if it gets heated, and then you get an unclean cut. So it would be better to have the mist on there, but it's also messy and we don't have it enclosed. And I would still consider this team to be sort of beginners at the whole CNC process.
Beginners, wait a second. I was thinking that you guys should be hiring yourself out for contract engineering and model shop work.
They'll get there, I'm sure.
No doubt.
Yeah.
That's the goal.
But you know, it takes hours to set up one of these parts to cut, and many mistakes are made. So it's a developing skill, but you know, they're pretty lucky to have those kinds of tools. And they were hoping to sort of power it up for the first time and show you guys, but I don't think the assembly is quite going to be there.
Oh, it's done.
It's done? Well, I don't know. You don't have a way to mount it or anything.
Have faith, Obi-Wan.
Yes.
Is the
Cooper's strong arm.
Is it working? Jose, can you stop presenting for a second? Jose, can you stop presenting for a second?
I pressed the button to do that.
Oh.
There you go.
So hopefully this is our screen showing up or just the camera?
We can each select what we want to see. So on the recording, I've made it so that the Iron Rain screen is showing the guys in the lab.
Oh, okay, cool. Oh, wait, are you actually going to spin it up?
Yeah.
Don't be in front.
You sure it's going to go the right direction?
Watch it like actually working and watch it say 4 meters.
Don't aim it at the camera.
Do you have your ice shield on?
Oh, it's going backward.
Well, with that effect, it doesn't matter, right?
Huh? Well,
Jam the plug-in backwards.
Oh,
okay, it's shot. It's on a very low battery at the moment, and it's geared down too much. But,
wait. I'm just amazed by the fact that it actually worked.
huh? It was shooting backwards too.
Yeah, it doesn't even have like on the exit. It has like a wall flattens out, so they didn't even have that.
Yeah.
This is way more sophisticated than our last launcher, which was like a piece of cardboard duct taped to like I think a rubber band.
That's true. There has been some progress this season.
I hope so.
That's
You gonna call this one the Wayne Gretzky?
Well, so I don't know if we explained the actual context. Do you want to do that, Bonavia? Like how far it has to shoot, how high it has to go, that kind of stuff?
Yeah, no problem.
It looks like it was compressing too much.
So, like as I mentioned earlier, one of the big things that we have to do in this year's challenge is that
More than we expected.
so we have to get the ring through that flywheel. That's the subsystem name, and then after that, it has to go in a projectile arc and then pass through this gate. There's 3 levels to the gate. We're aiming to get it into the highest level of the gate, which gets us the most points.
Compressing it more than I expected.
So one of the biggest goals that we've had is when the ring is flying over, we want it to be at the right summit. So in other words, we want to make sure that when we launch it from a certain angle, we're able to get it right through the goal. So the ideal distance that we plan to launch from is from 2 meters to 2.5 meters. So let me pull up the calculations for that. Okay. So the reason that we want to start aiming at 2 to 2.5 meters is because of the actual distance we have to travel. So 8.7 meters is the height of the actual gate, and then 0.41 meters is the height of our robot with the launcher mounted onto it. And taking the distance in between it into account, we get 0.47 meters. So what we did is that we represented all of this into a projectile equation. Let me send it in the chat so y'all can see it. But basically, it was a pretty simple equation. We represented it for vertically and horizontally. The big goal of the equation is that we wanted to find a decent launch speed for vertical velocity and horizontal. But on top of it, we also wanted to check if the RPM we had was decent, and we knew what angle we could launch at. And we could plug this equation directly into the code, and the code would figure out the rest for us. All we have to do is make sure that the angle of launch was consistent. That way, the ring would go with the exact arc that we wanted to go to and through the right distance. So give me 1 second. Let me get the equation pulled up so y'all could see it. Let's see. Okay, here it is. So this is the equation that we have for vertical. Okay. Copy. Okay, there it is. All right. So 0.88 over here represents the maximum distance, and 0.41 is our minimum. On top of that, we also took an acceleration due to gravity into account, time, and theta, the angle of launch. The big question here was figuring out how to get time, but we eventually figured out that regardless of the distance that we launch at, time is going to be reliant upon the height of our summit. So what we did is that we tried to find a time using the acceleration due to gravity, which made the equation a lot simpler. The aim right now is for this entire launch to happen over 0.2 seconds. So taking all this into account, we came up with a list of measurements. Jose, do you think you could share your screen to the final slide, which has the measurements on it? All right, sweet.
And by the way, I've muted about everyone who's not talking so that we get good audio. You might need to unmute yourself if you want to talk.
I think you can come now. Okay. Yeah, let me skip to the end real quick. I'll come back to these slides.
Well,
Here you
welcome to Vector Mechanics is all I've got to say. That's exactly what's going on there, right? Awesome.
Okay, so under here, we have the 3 different measurements that we want to go for. First of all, the most important one is the angle of launch. At 2.5 meters, if we want to make sure that the actual ring travels 2.5 meters, we have to launch at exactly 39.486 degrees. So obviously, we plugged in these values into the equation that we had, worked backwards using the horizontal velocity equation, and we were able to isolate the values for the angles. If we were launching at 2 meters, we'd get 52.645 degrees. This needs a little bit tuning because our aim was to ensure that the angle of launch was just below 45 degrees, so the launch could be a lot more consistent and accurate, but we're working on fine-tuning it so we can get it to that value. For the muzzle velocity, we got 58 meters per second, 27.58 meters per second for 2 meters, which sounds like a lot, but the average speed of a really small frisbee is 31 meters per second. So 27.58 is actually like a little too low, but we believe that it's fast enough to get us through the arc that we want. At 2.5 meters distance, we need 27.12 meters per second. The reason that the velocity is a lot lower when we're aiming at 2.5 meters per second is that when we're launching at a lower angle of launch, the launch is going to be a lot more accurate. And because of this accuracy and like the angle that it's being launched at, it's actually going to go up a lot faster than if it were launched at a higher angle. And because it's going a lot faster, it really requires less velocity to be able to make this higher height. So 27.12 meters per second was what we got for velocity. As for the RPM, so the revolutions per minute of the flywheel, for 2 meters, we got 367.7 revolutions, which again seems like a lot, but the average frisbee spinning through the air for about 5 miles takes 2,500 RPM. And considering that we only want our thing to travel 2.5 meters, this is like this is a pretty reasonable RPM to aim for.
Did you say 5 miles?
I did say
miles.
I don't like using miles. I am very strictly metric, but I googled this up before the presentation, and the website that I had miles in it, so I was like, all right, I'm just gonna go with this one. So at 2.5 meters, we got our RPM of 361.6. Now the biggest challenge out of all of the calculations that we've gotten is plugging in the exact equation we have along with the time into the code. Yeah. What we do know that the computer can do is the computer can keep track of the time. I hope I got that right. So the computer can keep track of the time. All we really have to do is adjust the angle and the distance that we're launching from, and the code will take care of the rest. So, and having all of these calculations is super helpful because when we want to make it go to the third level, we can't just rely on
the right so that it's like right. Yeah, it's right up against that.
So when we're launching it, we can't rely on sheer dumb luck and hope that it gets through the distance we want it to. We want to make sure that the launch is as accurate as it can possibly be. And to do that, we have all of these calculations beforehand. Because Jose did this entire project in CAD, we were able to get the diameter of the flywheel through the CAD, which I was able to plug into the equation to find the exact angles of launch and the RPM and all that. So having all these calculations prepared and set up earlier makes sure that every time our launch happens, it's going to be as accurate as possible. The next challenge is just actually implementing this into the machinery of it. But yeah, that's the gist of it.
Cool.
So have you actually tested this formula in real time to see if theory meets reality?
That is what we're in the process of doing because Cooper and Paul are getting a subsystem mounted onto the robot right now. Okay. And once that's done and the code's ready to go, we'll be able to test it. Hopefully it does work reasonably because the angle of launch and the RPM seems to be at what we want it to be. So given that the approximations are as close as they can possibly be, it's a good thing that it's likely that the launch will go as we expect it to.
That's not duct tape.
Because I was going to say, it's been a while since I had physics in college, but I keep thinking there's the sine, cosine, you have, arc angle and all this and that. And I don't remember the formula that well. So
yeah, to be honest, I forgot most of geometry after I finished it in like 8th grade. But like since then, all we have to do is like pull up like the ballistic equations that we've learned through physics and all that, because all of us are in college physics right now in our schools, and so we were able to, you know, like draw inspiration from that to make our like equations work out fine. But the main goal was that we wanted to have this equation set up before we did the build, so then the actual transition to testing would be a lot more smoother.
Benavia, I can say one thing is that you should be at least expecting that within 10 or 15 years, you'll have forgotten all of this, just like we have.
Not unless we stay in the field.
I mean, I'm fully prepared to accept that. About like a month after we covered ballistics in school, I completely forgot about it until Mr. Verani brought it up for robotics. And I was like, oh, what we did in school applies to engineering.
You know,
You'll be fine.
I'll agree with Murray on all that stuff, but I'm going to take a more positive spin on it. You may actually forget some of the nuts and bolts, so to speak, but the theory and how everything works and all that other kind of stuff will stick with you. I'm 55 years old, and I understand everything you were doing right now, even though I might not be able to recite the equation. I get it all, and I understand it. And I think most people on this tape and on this talk will get it all as well, and so will you. And you'll never forget the concept. The mechanics maybe get a little rusty, but the concept will never go away. You got the idea. It'll stay with you. I'm pretty sure about that.
Yeah, there was one professor I had one time, and he basically said that college was basically learning how to do research, that you don't really memorize everything. You just have to know how to go about finding the information. So,
I'll take you a step further because
learning how to learn.
Yeah,
I'll take you guys a step further in the learning because, you know, once you learn enough, then if you can just hire a group of high school students that know what they're doing and build your model shop for you, then you don't need to know anything.
Well, there you go.
Just hire them.
No,
Okay, anyhow.
no, you still need to do your PDS.
That's true.
Your
I
slides.
mean, no, it's good to learning. It's really impressive what you all have to show. So, and the demo, and there's some live metalwork or sparks flying in the background. That's pretty cool. So,
Yeah, hopefully they all have safety glasses on. Thank you. But yeah, I guess it is a good thing. So last year we were all underclassmen on our team, and all of the seniors had graduated. So most of the stuff that we did, like when it came to testing, was like trial and run. You know, like we make a couple of shots, hope it goes through. If it doesn't, we try again. So it was all like completely based on like random sheer dumb luck, and somehow it kind of worked. You know, it got us through like the level of the competition we wanted to. But this year we're trying to like be a little bit more organized about our planning, and we were able to do that especially through the virtual setting. So Jose actually coded almost all the subsystems that we needed for CAD before we started the build. We already had a CAD from the robot model last year, and so that made the actual build of the robot a lot easier because we were able to like carry on the steps over. A lot of our parts are custom printed, which we were able to get done through CAM. And then even on like the little subsystem, there's like a little red rule, I think that was also CADed in NinjaFlex. And Trey modeled a couple of intake systems so we could test those out beforehand. And then obviously we had the modeling of the equations. So being online has been hard for the most part for robotics, but the nice thing is we've been able to like get a little bit more on track for our planning when it came to build.
So I have a question on regard to the disc. So when you shoot it out, is it going to go straight, flat, or does it have to angle? In other words, is the hole that you're aiming for, is it a round hole, square hole, or sort of the general layout?
It's like a slanted hole. So I guess if I could like demonstrate how it would look like, it would kind of be like a pocket. So if we take this to be like the outside of it, then there's like another wall covering it, and it has to be aimed in between them. So it's kind of like a post box, I think is the best way to put it, or like a mailbox.
But it's not exactly perfectly 90-degree angle. In other words, they
No,
got
I
to slant
wish they were.
to give you a little more challenge. Okay.
Do you have a throughput requirement, like how fast you need to shoot?
We do not, but we do have a maximum requirement. So, for instance, the maximum height that the thing can be launched, I believe, is, hold on, let me make sure that I'm getting this right.
I was gonna say we do
yeah.
actually have a minimum. So there's like Like 5.5 feet away from the goal, there is a shooting line, and you can only shoot from behind that.
And the
I
height of
think
the
I think
like
it was
little
the
ring.
How many discs per minute type of throughput?
Oh, no, we don't have any requirements for that one, but we're just aiming to get like, a speed probably around 25 meters per second, because that point is fast enough where it's likely to like go far enough to where we want it to, even if it's not completely accurate. But we
I
do have
don't
a requirement for height because we can only go to a maximum of 5 feet, which rules out the possibility of having any driver below 5 feet tall or at 5 feet tall.
So, Bonavi, I think you misunderstood the question. If you guys can see my screen, I'm pointing it at the goal. So it is this rectangular slot right here, and that is the sort of the high point target that they're trying to shoot through. There is a goal about the number of rings you can shoot per second, but it tends to be more governed by how you can recover those rings from the field. But the point scoring here during the teleoperated phase is all about the number of rings that you can score. So you want to do it as fast as possible. But we don't know that, like, they haven't got to the point where you saw them assembling the shooter for the first time. So it's not under software control yet. And they haven't got to the point of connecting it to the intake. So they don't know how fast they can cycle the shots. But they want to cycle them pretty fast.
I got you. So what I heard was that there was a lot of ballistics, and you're looking at height and all that kind of stuff. And I think that's awesome. I guess you're going to make an angle and go into it. Have you ever thought about powering it enough just to shoot it directly at the thing? Get it on the upswing instead of on the downside of that thing. Can you put enough juice on it to make that happen?
So,
you understand what I'm asking?
Yeah, no, I get what you're asking, but and I'm probably not the one who should be explaining this. So,
Okay.
if Benavia wants to take another crack at talking about the summit and how that's the flattest part of the trajectory.
Yeah, to be honest, I didn't understand the question super well. Do you mind like explaining it again?
So in ballistics, you have a parabola kind of thing working for you, right? When you
Yes.
shoot, it's going to have an apex and that kind of thing. So have you thought? I was thinking on the head. I mean, there's a couple of ways to do that. You can plan on shooting it and make the apex just after and know where that's going to be, or you can make the apex the slot.
Okay, so we're making the apex a slot in our equation, which is why we divided time by 2. In the equation that I sent, if you notice, sine theta uses time divided by 2 when it's being multiplied. The reason that we took the apex to, the reason that we took the goalpost to be the apex is because we realized it would be a lot more accurate that way. If we were to say that it went through a complete arc, it wouldn't actually work out because the robot itself is already at 0.41 meters when it's shooting. So a perfect arc would require that the place where the goal reaches to also be at a level height, which wouldn't happen. So we realized that an apex would make sure that we're aiming like up high like this. So which is why we wanted the angle of launch to also be 45 degrees so we could better get to like that exact point.
Cool. I was just wondering if you'd thought about those different things. I don't really have an answer. I was just posing a question. So awesome that you've thought about all that stuff. I think it's fantastic.
So that slot is 8 meters up, so 26 feet.
No.
Oh no, it's 0.88 meters.
Oh, I thought you said 8 meters. I was gonna say, wow, that's pretty high. Okay, that explains something.
I'm thinking maybe it's important to be repeatable. Like if it's repeatable, then then you can reproduce your.
Yeah, because
your-
ideally we're shooting like 20, 30 rings per match. So
Right.
So
that's-
you fill the thing up, or do you have to go collect them and refill? In other words, do
yeah,
you do like 10 out there?
there's a carrying limit of 3, but there's a total of 10 like in circulation. So it's really about how fast you shoot them off, but then also like how fast can you get them back into your robot to shoot them again.
Yeah, there should be a sort of maximum benefit speed versus time thing.
And during the competition, those rings are going to be used hundreds, if not thousands, of times. So the anticipation that when you were squeezing it too much over there, maybe not squeezing it too much, because who knows how much how much your roughing or damage or smoothing is going to get happening to all those rings that have been wrapping around. Maybe you want the extra squeeze on that. I mean, I'm just thinking out loud.
Well, no, that's a good point. I'm thinking that you're right, that you probably need some type of adjustment that you can do on the fly because of that reason. Because I assume you don't get new rings every time, right? I mean, they get reused over and
No,
over.
they do get reused.
So yeah,
Unless,
you might
unless we just
think of,
order new ones.
so you might think about some type of adjustment or being able to adjust relatively fast. May try
Yeah.
that out because that is a good
So
point.
the compression of the rings, so like the amount of space between the flywheel and the walls isn't exactly the 5 inches. It's more like 4 and like 3/4 of an inch. Just so there's an equalizer, like the ring will always be compressed. I mean, well, it'll always be like the same length. So there's sort of that to help compensate for that. But yeah, I do agree that there should be some what do you call it? Something to better.
Well, to adjust the
Yeah,
base
to
of the
adjust it,
wrist.
basically, yeah.
Because I don't know if you all have looked at like how they do tennis balls and that, where they have those things where they'll shoot out the tennis and that, and how they feed it between two balls basically. So
Ray just in comments, Ray called it adjustable squeeziness.
Adjustable squeeziness, yes.
Yeah,
Good
so
work. Fantastic.
on the motor that drives the flywheel, the mount for it is slotted, so we can adjust how tight the belt is. So we could use that similar idea for the outer walls.
The only concern about having a tennis ball launcher kind of deal would be accidentally hitting a coach in the head with a ring. But assuming that they're all taller than 5 feet, that would not be an issue.
right.
If they're at 5 feet, though,
I
then
don't
we're
know.
still
Hit the
getting a
coach.
penalty.
No, hit the coach. If he's in the ring, he's in the field of play. Sorry about that. You're part of the game. That's what I would say.
Those tennis ball launchers have a muscle, right? Like it goes through a tunnel.
Yeah, well, they're basically from the top down, and they have basically two reels spinning, and then it goes between the two reels to spit it out. Is
Does
how
it
they
mean
work.
that there's a like a passive portion?
And they look like they
After you-
effectively have one reel doing the spinning, and they're using the walls basically flat. So I was wondering how well that works because, yeah, they use on tennis ball they actually have two reels spinning.
Yeah. Well, they got Ninja Flex on there, so it's basically
True.
a piece of rubber rubbing up against another piece of rubber for lack of better terms, new word, gription. Okay, or friction in this case, gription. That's what. But that's a pretty good idea. That putting that TPU on that thing, that's a pretty good idea.
Oh, speaking of
Yeah,
the
those
Ninja
fins
Flex,
seem to grip pretty well. I like that. Somebody write that down. Gription is your new.
Gription?
Yeah, we're gonna start using that word.
That's
now.
a new technical term of the day.
Speaking of the Ninja Flex, like parts in there, I think Trey was the one who catted that. Trey, you want to explain the design for that?
The wheel?
Yeah, the little red thing and like the other stuff.
I think Jose actually designed that one.
All right.
Oh yeah.
Jose,
So what was the question? Sorry, I forgot.
No, I just thought it was a good idea of you guys using that
Oh.
flex, which is basically TPU, which is basically some sort of rubber against another rubber thing to get the friction
Yeah.
as high as you can. I thought that was a great idea.
So like yeah, so you can see the flaps that the flywheel has.
Mhm.
And like if it was a Ninja Flex, and like if you need a Ninja Flex in order to be able for those flaps to be compressed by the ring, just
Yeah.
gives more points of contact for the ring.
I thought it was a great idea.
Thank you.
Well, I'm sorry we can't show you it completely firing at its intended trajectories. Huh?
You can fire it.
Well, it's still going backwards, so and it's not under robot control. We're not quite there, and we've consumed a lot of your time. So
Hey, we just saw the first firing in the first assembly, didn't we?
Yeah, yeah, you did.
Well, let's have a big round of applause. I mean,
Yay.
come on. That's fantastic. Backwards, smackwards.
Yes. So
Really?
so we'll have the
Oh,
update
they
next
got it.
week, right? You'll have it
They
up and
got it
running by
running the right
next
direction.
Tuesday.
Our first
didn't log in,
qualifiers
what-
in like late February.
We are gonna try a test shot real quick. Can you like angle it up a little bit? Where's it gonna shoot? Huh? I gotta get back here so I can see it, or so we can see if it goes anywhere.
No coaches were harmed in this.
All right, go ahead. Yeah.
Yo.
All right. Nicely done.
They may have to adjust the what do you call it, the gear
The
ratio
speed.
on that motor. They can still speed it up by 3 times if they need to, but it looks like it's pretty close.
Yeah, so like usually a 0.5 to 1 ratio would be used here, but we have a larger flywheel of 6 inches, so we can handle having a slower motor.
I'm just thinking you guys might want to commercialize this thing because I might want to buy one just to keep my cat off the couch.
Yo.
What was it? A year or two back, you could get those little Nerf things that they have, and there's 1 or 2 instructables where they convert those to be.
I think you need to angle it a little higher. Gonna try a couple more shots real quick.
Ooh.
I thought the flipper wouldn't actually feed into the flywheel properly, but yes, it does.
That seems pretty consistent for a handheld shot. We'll have to see.
Let's go.
So is that
Not
the
one.
about 10 feet or 5 feet out? It looks like.
No, they were shooting. That was about 12 feet.
Okay, because we don't have stereo vision, so it's hard to see depth.
That shot was about 12 feet.
Not bad.
I tried timing the launch. I got 0.7 seconds, so not bad.
Yeah, but you still have to account for the fact that like somewhere in between that arc will be the actual goal.
Right, and also like feeding also takes a little bit of time, and for it to like actually reach the NinjaFlex spinner.
Because
flywheel,
that wouldn't count in the calculations.
Right. But they do have cats, so I feel like at the end of the season we can use it as a cat toy.
Cats. Yeah, they're cats.
Or a human toy. I just feel like a frisbee launcher would be pretty cool.
Even better. Would we have to jump up and catch it in our mouth?
I mean, whichever works. You know, if it works, it works.
Well, pretty impressive, guys.
Well done. Yeah. Did you have any specific questions, or you just wanted to walk through it tonight, or?
We kind of wanted to like show you guys your subsystem, but I do have one question, more about like the actual launching. So originally we were considering taking air resistance into account to make the calculations a little bit more accurate. But the other thing is I genuinely have no idea how to do that. Do you guys think that like taking our air resistance into account into things like this kind of a launch would be a good idea?
There's a lot of thinking going on here. A lot of thinking.
The only thing that occurs to me is, which would make it much more complicated, would be to have a video camera, looking at the goal to see where they are in relation. So you basically would actually keep a log of the machine as it's launching these things, so you can see the power going to the motors, and monitor that at the same time as you see a video camera of that particular ring hitting the target or not hitting the target. And maybe you guys could graph the difference and see if you could then run a dynamic air controller on that to either ramp the speed of the motor up slightly or slow it down. We've had an ongoing discussion of PID controllers, proportional integrated,
Get it.
you know what a
Murray,
PID controller is.
cut it
I had
out.
to bring, but you could put a PID controller on the motor and then basically have the dynamic air control on the results of the firing at the target, basically feed back into the PID controller, something like that.
You're good.
So
Unity,
actually, we have a slight plan for that. We've got a camera on a robot that's going to be positioned basically kind of like you were saying on the shooter itself, and we actually are going to be developing a custom vision pipeline that we're probably going to use TensorFlow, but we're going to be doing continuous, continuous semi-autonomous, like I guess finding of the target using a, well, it's not on here, but a printed label up here, and I guess odometry just in case we lose the vision target. We're going to be training that sometime. We got to develop the pipeline first. Well, yeah, it should be continuous tracking of the target, and that could also help, as you were saying, with like trying to have it like positioned properly for testing. But we could probably just test the pipeline and the shooter all at once to try and, you know, accomplish the final goal at a faster rate instead of doing 2 separate tests or whatever.
Sure, yeah, because I was just thinking you're not really tuning for left or right so much because that's the position of the robot as it relates to the target. But in terms of that up and down, basically you could just start speeding the motor up until you get to the point where you can see exactly where on that speed range you're getting to the target at that particular distance, and then start tuning on that.
You could also, in theory, keep it at a constant higher speed and use the angle, right, to figure out. It's going to be a parabolic arc, like pretty much always. Yep. So in theory, you could use that angle and try and figure out, like, you know, the parabolic arc, and you'd want to, I guess, reverse it so that you'd find the distance, the parabolic arc, and then the angle.
Oh, I didn't understand. So you guys can actually alter the angle of the launcher on the robot?
Yes.
Yeah,
it's going to be
okay. Okay.
The bit question would be is.
Yeah, they got lots of knobs and buttons and things to turn to figure out which.
So the key thing will be is to be able to achieve that. You'll have to have a certain speed of that disc will have to go out. Otherwise, you will get variable. So I would say,
So there's a mathematical way to approach this. So when I went through Six Sigma training, it was called design of experiments. And what you would do is, since you have these different controls, you've got the angle, you've got the speed, you've got the distance, you've got the different variables. So what you would do is you'd set up the so-called design of experiments, and you'd take measurements at a couple different points. Then you would kind of linearize them. So you're familiar with the term and the process?
Yes.
Oh, cool. You got the design of experiment,
right?
Sorry?
I believe we covered it in calculus, AB.
Somewhere in there, yeah.
I don't know. Well, this one's it's a more of a like Doug's shaking his head. It's a separate thing.
I thought you meant linearization. I'm sorry.
No. Design of experiments, or DOE.
DOE, but I think Doug, the DOE does use linearization in there. But what it does is
it depends on your model. But what I'm saying is that is an area that you would really be interested in. It would open up a lot of things. One of the things that it's a good approach is how to get the most information with the least amount of tests.
Yeah.
It also tells you the strongest variables that you have to worry about. Now, but so you might want to just put that down to look up and study a little bit, DOE, or design of experiments.
I am? Yeah. Sorry.
The other thing, though, is, you could probably, without too much trouble, actually, if you've got, do you have a camera? You say you have a camera pointed at the target?
Yes, sir.
You probably could make a sight, basically, and use the sight to sight in, because you probably also have sensor distance measurement to sensors on the front too. You're only talking 2.5 meters. Um, to be quite honest, that's so close. That's only what 500 centimeters apart, so that's roughly 18 inches. So I would be surprised if you
If
probably.
we actually got that parabolic action in there, it'd just
No,
be more of a
I was
straight shot.
thinking, I saw the angles that you said. One was 50 something degrees and the other one was 30 something. That I would be really
39.496.
I'd be really surprised they're that different.
Okay, yeah.
You know, and also just an engineering rule of thumb. Probably anything after the first digit is vapor. So don't even worry about that in your calculations. You'll think you'll get error creep, but in actuality, for something like this, you know,
Everything's got to be fluid anyways.
3.375, 53, probably good enough, you know, unless they're real close. You know, if you find out one is 54 and one is 52, then you probably have to go a little more. But with a distance sensor and a camera, yeah, you should be able to make a real simple sight and just clue it in. Now, what would really be cool is, your driver is going to be under a lot of pressure here because that slot. How wide is it? It didn't look very wide.
Oh, I guess my my forearm's just about a foot, I suppose. So 18
Yeah.
inches. It should
Yeah,
be large enough.
Yeah, what would be really cool, and I know this is probably way down on your priorities, but is if you could have it autonomously give you a lateral correction because you got a camera. It could adjust, if your driver could just get it close, you could let the robot do the final tweak in the
That's what I was. Sorry,
Yeah.
that's what I was saying earlier. We're shooting for semi-autonomous tracking of the goal here, and actually we're using distance sensors on the robot right now. But I think what we're going to do is, in actuality, probably just use odometry, and get rough coordinates, right? And with rough coordinates, we can, in theory, point the camera to where it should be. Eventually, well. We
Let the
will
camera
have
drive you.
yeah, basically,
Let the camera
yeah.
drive you.
And then eventually, once we back up to past the shooting line, we should be able to have the target in our viewport, and then we can actually, start to I guess correct for errors in odometry. In theory, later down the line. I mean, obviously, doing all that. Though it is interesting to note that with one of our vision pipelines or vision providers that we're actually using, not necessarily the one we're using for this one, but it could be something we could look into. It's called Vuforia. And Vuforia actually has, in its API, it can give you approximate distances and angles in XYZ and roll, pitch, and yaw relative to the viewport. So in theory, we could also use that as a fallback if odometry fails and we decide to go with Vuforia. As I said, we're probably going to go with TensorFlow.
Yeah, you might also look at the new Oak D that just came out. It's it provides depth information from a camera because it's got stereo.
Nice.
I'm not sure. They finished. They're delivering on their Kickstarter, so I don't know if they're in production yet. But you might want to take a look at it. It's Oak D.
Okay.
So
we will.
That might be. Well, that's kind of. This really looks good, and you know what? It looks like you got plenty of power on your thing to throw it further than you need to. So now you just got to be able to aim it. So it looks
that
good.
and also have charged batteries because if our voltage is constant, then our speed is also constant.
Mm-hmm.
Well, yeah, our velocity.
Yeah, so here's
You
something
could also do correction for that.
consider. I don't know what your limitations are, but if you can over voltage it and then control it, use a voltage. What's the word? You can drop the voltage down a bit below your maximum voltage, so you have some headroom for your battery to go down without losing the delivered voltage. Okay, and you know, you can also, it'd be also interesting to measure your current cycles to see how each current cycle goes per each run, because you might even be able to use a PID loop on your current to give you a little boost. So like if you get a sticky one, for example, you know, what happens then? It'll be interesting. You guys are, looks like you got a really great challenge, and it looks like you guys are really doing a good job.
Thank you.
We're gonna want I know we're going to want to see you guys come back when you get this all working. Yeah.
Yes,
Who's
sir.
the driver, by the way? Who's going to be under the gun on all of this? Who's the driver? Do you have an assigned driver now?
We have a temporary driver who is the most likely candidate, Jose, the catter,
Okay.
who is probably, he's very good at driving. Don't get
Okay.
me wrong. I don't mean to insult him or anything. We're looking into our options.
Okay, gotcha. Yeah.
Drive practice is historically a problem for us.
Yeah.
I can understand.
Practice during competition.
Yeah.
That's part of the benefit of having everything like pre-CADed and pre-designed and all that, because then you're relying less on driver error to get you through the match and more on planning.
How do they return the rings to the floor? How do they, once, let's you shoot one in the goal, how does it get back out on the floor? Does it just
Very good question.
So there's actually
Let's say we actually, it's hard to see where I'm pointing. Let's say we get a ring in here, right? It goes down into the goal like that. There is a human player that stands behind here, behind this goal. Right now, we don't obviously have the space for it, but we will. And then the human player, and I think you can see this. They put the ring into this little side thing here.
Mm-hmm.
Hey, mind? You put the ring right into this little side thing, and it rolls back into the thing. Did that come on camera?
Yep.
All right.
So you have, do you know how many rings are in play? You said 10. Is that correct?
10.
Or,
yeah.
Huh? So there's 10, and you can each stack 3. So in theory, 6 of them could be stacked, and only 4 on the floor.
Well, there's only one robot in remote play.
Oh, aren't you? Okay. You don't have teams. Gotcha.
Yeah.
Okay.
Not until we get real traditional gameplay back, which is COVID dependent. So right now, we're all doing it remote from our own locations and just videoing the match. So right now, it's just one robot on the field at once. Otherwise, it would normally be 4.
Yeah, that's what I was thinking. I was saying that sounded like that would be a scramble for the rings. But
if it's 4 teams, it would be 20 rings on the field. But there would be a lot more interplay, I think.
Yeah.
That's where defense comes into play.
Now, are they going to set up, Kareem? Are they going to set up a arena somewhere, and you guys are just going to have scheduled times that you go to do it?
Yeah.
When you're doing remote play, you've got your own, like we've got our own arena here. It's a mess. It's full of boxes, but we can clean it up. Some teams will not have even a makeshift arena. And so, for example, we will open up the space for other teams who need a place to tape their matches for a competition. So the competition is now going to be about a week long, or at least like 3 or 4 days, in terms of the span of time where you can get your matches in. It's still scored online and it's still real time, but then you can submit your video later, and you're going to have a span of days in which to actually film or run your test matches.
I got you. So it is live. So like when you decide,
it's not live. The robot game is not live. The only thing that's going to be live is the judging.
Ooh. So like if you guys could do it 100 times and have your top three videos.
No, it doesn't work that way. So so there's an online program. So once you begin it, you can either run a test match or a real qualification match. And it'll record the scores that you submit as you're going. If you run a qualification match, it could still be gamed. There's no doubt about it. But we're relying on an honor system, and the people involved in this. I think they're going to be trustworthy.
Yeah.
Hey, one more item back on the question of modeling aerodynamics and how that led to the design of experiments. So it strikes me that with these kinds of things, there are some controls and variables which have a lot of effect or not much effect, and then there's some control variables where you make a tiny change in the control and you get a big or widely varying change in the output. And the cool thing about this DOE, if you can figure out how to drive it, it's relatively simple once you get the templates going. The cool thing about the DOE is that it helps you understand which ones have the biggest impact and which ones have the really narrow sensitivities. And the cool part about that is that once you learn how to read the charts and of your results and map them out, is that you can center the design. So that what it means is that those things that vary a lot that are hard to control, let them vary, because you're going to pick the design that says you're going to hit the target even with the variances you have in the system. Does that make any sense?
Yes.
Hopefully,
so under the DOE, does it make a difference if each of the variables are measured through different like systems?
No, that's the beauty of it, you see, because and I put some links in there I just found quickly during the call, but the DOE will help you no matter what the units are, no matter what the range of numbers are. It takes all of that into account. It kind of maps them all into the appropriate ranges, and then that's what I say by linearizing. I don't know if that's the right term or not, but it helps you bring all those into the same way of thinking about it statistically, so that you can then, with a relatively small number of measurements, like Doug said, you can understand the whole control space, and then you can pick, like, if not the optimal, you can pick really good answers with only a relatively small number of measurements. It feels like magic once you do it, but I haven't done it since the training where we did a rubber band based catapult, and that's how we learned it on the job. So Texas Instruments, exactly. Yes, that was the one.
Because they have to make tests on machines and material, and it's very expensive. So they want to do it in the least amount of runs in the least amount of time, and so they're very big on DOE. There are, Kareem, don't you have Texas Instruments as one of your sponsors?
We were trying to get Texas Instruments. They sponsor some other teams in the area.
Yeah.
And I think that they decided to stick with those teams.
But you might be able to ask them for some DOE documentation.
I'm sure we can.
They got textbooks like, that, they're really good stuff, because they're meant to explain it to people who haven't been introduced to it, and they do really good. So I'm just saying, if you can.
Yeah, no, the team will look into that. That sounds great.
Hey, for what it's worth, check the last link I just put in here. There's a 69 slide share on the catapult DOE experiment. So it may very well give you some ideas on how to do it.
Yep.
Unironically, a catapult design was our very first like prototype for the launcher, so I feel like we'd be able to like use it as like a good base for the next flywheel system.
Because it's really similar math once you get the object in the air. And then another one of the links in there had an Excel spreadsheet as a template for setting up a DOE.
Yeah, there's many different DOE designs. You have to find one that has the right number of variables that you want to test, because the intent is to have all of the variables what they call orthogonally opposed to each other. That's why they can get away with the small number of tests. Anyway, it's definitely, Carl's right, it's definitely something to you guys, if nothing else, it will broaden your knowledge. You guys will really enjoy it.
And if you tried it and you've documented, boy, that's going to get you some serious points in the, what's that one, innovation category or whatever you have?
Inspire and Think are the ones that are documentation.
Yeah, if you brought DOE and no one else in the competition has done it, you'll knock their socks off.
Yeah. Well, everybody's going to know about it now because this is going to go public.
Oh, that's only if they watch it.
That's true.
Well, glad to have you on board. Thanks for presenting. Big round of applause for our favorite high school team. Go Iron Rain.
Thank you so much for the feedback, especially for the documentation bit. One of the challenges like of the Think Award is that we have to be able to document like robot mechanisms, but in a way where you can understand it like computationally. And I think a DOE would like really help with that.
So in about a month from now, give or take, you'll come back and show more detail how it worked.
Kareem, if you guys, I don't know how.
I don't know where your schedule's at.
Some info. I'll put it up on the website as you having visited this meeting. Do you understand what I'm saying? So that you guys, well, I just to document that you're here.
Your community outreach points.
Oh, sure. Yeah,
okay.
Yeah, that would be great.
Okay.
Thank you.
So we'll do that, and we'll get something up on the website about this meeting and your visit. But I got to admit, I haven't been fully paying attention on everything because I've got some distractions. So if you could send maybe one overall CAD picture and maybe a couple of slides from the slideshow. You don't have to send me the whole thing, but whatever is easy. And I'll extract information and put it in a post. Okay?
Sure, we'll do. Thank you.
Okay, and I won't give away any secrets.
No, it's all right. It's all right. I was joking before.
Yeah.
It's better when this information is shared with all the teams.
Yeah, I know what you mean.
Okay. Thanks everyone for helping us out here. You can return to your regularly scheduled programming.
Well, this is it, Kareem.
Did we take up the whole? We took a lot of time. Wow.
Don't apologize. This is a great discussion.
Otherwise, Kareem, we would have just been talking about PID controllers this whole time.
Yeah, the whole time. Because that's actually the top of my question list when it's my turn. Okay, good deal. Well, we'll swing around then. So, so who would like to go next? Or does everybody want to hear my big question? Oh, Pat. Pat raised his hand. Good.
Yeah, I don't have much today. I did, thanks to Murray who posted some code. I went through and had a look at and basically after about a day of looking through that, I put away my robot and I started playing with my Legos because I realized at what potential I'm at for programming. It's hats off to you. You've gone really in depth with your code, your robot operating system. You've taken, Murray, you've taken a lot of effort into that software. It did help me out tremendously. So I am actually able to get joystick readings into my robot, and I can process them. And I'm looking at it. So my next hiccup is reading 2 joysticks at the same time. So that I've got an X and Y or an X and Z translation.
But that's what I'm doing.
Yeah, so I am, yeah, and I'm right now, the way I'm doing it with my EV dev, I'm not able to pull them both in at the same time. So I'll have to take a look through and see what else I can do to pull them both in and then transfer over to my other program. Following through your logging on your program really helped me out. So I started putting in some logger in the program, and I'm able to see what's happening in the different routines and print it out to a file and able to follow through after that. But after following you and then seeing what the kid's done, I'm lucky I'm feeding myself with a fork. I'm lucky I don't poke an eye out. So that's my plan. So this week I'm going to work on getting a couple axes pulled in at the same time and get those sent over to the main Python routine. And I have that already communicating with the Arduino on the motor routine. So that'll work good. So it's just a matter of doing a little more fiddling and finding out how to pull both in at the same time.
Yep. Sounds good. I mean, it's funny looking back over all that code. I mean, as I think I probably posted in the mailing list, is I'm an infrastructure developer, so I have been for years. So I kind of over-engineer everything. But looking at all those classes that I wrote, the ones that are actually to me the most valuable is probably the logging one. There's a config loader that can read from a YAML file for configuration, and I mean, there's a few others, but basically just and the gamepad one that can read off of one of these little Bluetooth gamepads. But anybody can repurpose that stuff pretty easily without taking on the whole thing. And I'm glad to hear at least you are doing that, because it's hard to tell if anybody's using your code.
Yeah, so I went through and then just basically got the basic structure of how you're working through it and was able to pull that into my my program. I didn't grab the whole thing, but I just basically look at how it's working. So that's been good. I've got a little more hardware to do. I've got to get my encoders rewired. So my old encoders were using just one pulse. So I was only getting one channel of the encoder back. So I'm going to add the second channel in and pull that both in so I can get a bidirectional signal off the encoders. So I'll do that probably on the weekend, and I'll keep fiddling away with the gamepad. It's the one I've got. It's a Chinese one, and it comes out as an Xbox. So I've been basically working through my code on that. I created a mapping table for all the keys. I'm not going to use them all for now, but I'll probably set them up so that they're able to use. And then, like I say, I need to be able to get in an X and a Z axis at the same time so that I can control, velocity and an angle. So thanks for the help. It was good. Like I say, I'll keep my safety glasses on when I use a fork.
You're not alone in that, Pat. We're all with you there.
Oh yeah, it's just looking at everything you can do. But like I say, probably one of the biggest things was the logger. I said, I should have put a logger. I've seen it used before, and I've just never done anything that complex in Python. And I said, okay, it's time to put a logger in, so I know what routine, where the values are coming from, what's happening. It makes it nice.
Yeah, and anybody listening in on the call, I mean, there's just one single logger class, and if you put it in a lib directory, you can look at any of the test classes that are just anything with test in the name in the ROS home directory, and then you can do kind of standard like Java or you got like debug, info, warn, and error log levels. And it's very similar to just other loggers I've used. And there is a logger in Python, but it doesn't give you as much functionality as the one I wrote, because I wrote this for a purpose. And there's a feature in there, which I haven't used in a long time, which actually outputs data to a CSV file. So you can actually get CSV output from the logger and then put it into a viewer and actually take a look, visualize the data. So.
Yeah, that one I was thinking of doing was the CSV file was when I start tuning my PID loops to basically, now you can have it roaming around on the floor, in real world conditions, and be able to log a CSV file and then take a look at it after, plot it out.
Yep.
So your logger class is written in Python, or is part of the ROS stuff?
No, I mean, I named my robot operating system ROS because it's a robot operating system, but it's not uppercase, it's lowercase, and it's not related to the ROS project at all. It's just a small Murray all-time Python project with several dozen.
Ross.
It's called ROS mistakenly. I thought about calling it, because my robots are all with a K in them. I can't even remember why. So maybe I was going to call it Cross, but that sounds kind of stupid. So I just
I
left it.
was going to ask you that. Why the start with a K for all the robot
I
names?
can't even remember now. I'm trying to think why. David's robot starts with an SR and stuff like that, and I thought I'd call mine K for something, but it has nothing to do with New Zealand or something. I can't frankly remember right now.
Okay.
I'll probably have it on my wiki.
I'm not using Murray's. I'm not using Murray's logger. I'm just using a Python logger.
Yeah,
and
that's fine.
Log everything to a file.
All
And
my
that,
projects start with a little bit of profanity. So that's, I don't know about how you guys label things, but that's how mine start, one way or another.
Murray, the first time I ever brought my robot to a DPRG contest, when we were entering the contest forms, they said, "What is the name of your robot?" It had never crossed my mind to name my robot. It was just the robot. You know, my car is the car, the broom, lawnmower, the robot. So I had to come up with a name, and at that point, it was software revision 404, and that's where SR04 came from. It's off the top of my head, but it stuck. And if you search on SR04, dozens and dozens of things out there are called SR04.
Yeah, I will tell you, my company Improving, we have these yearly getaways, and we're a fairly competitive bunch, and we like talking smack and all the other things, very much like the folks I'm in front of right now, as far as the talking smack about things go. And I come up with this set of words I say when somebody asks me. So if I was in your place and somebody goes, "What's the name of your robot?" Better than yours. That's the name of my robot. So I have confidence. I have confidence right up until I don't need to have confidence anymore that I'm going to be in the game, right?
Nice. All righty. Let's see. So would anybody like a control loop question?
Yeah.
Okay. So as it turns out, last week, aside from sketching out some thoughts and putting them into the telepresence robot chat, which we could do, but we might not have time for tonight. I also managed to get one of the Bosch BNO 055 IMUs. And finally, I actually hooked up all 4 wires that it takes to turn it on and ran some software. So I have it running. And the next step now is to duct tape it down to the little mechanism wheel robot. But this leads to the question. What I want to do is use it for helping with steering and control of the heading, because with the mechanism wheels, you know, you can't count on odometry. So the question is, what are the thoughts on using the gyroscope to, like, let's say I want to hold a constant heading as the robot's moving in any direction. Do I want to start moving and then adjust the velocity of the turning based on the gyroscope feedback? So do I want a heading velocity control loop, or do I want to use the compass if I'm in an environment where compass supportable, and then use an absolute have a control loop around the absolute heading position?
Don't do that near one of Chris's stairways.
Yeah. Not near Chris's stairways or somebody else's motors, or I don't know what, but.
Carl, this surprisingly sounds almost exactly like the question I asked.
It might be.
It was basically the same thing, that if I cannot rely on a compass heading, then I need to use the gyroscope and maybe the accelerometer. If I can use the heading, I'd use it. But as everyone has basically been beating me around the head with a stick for months, is that you can't use a magnetometer indoors. So I'm still on that one. But I think it was actually Doug Parody that pointed out the kind of basic algorithm for using a gyroscope and or accelerometer. But I think we're on the same track. We're almost in the same place. I'm not using mecanum wheels, but it's the same idea that once you've got that idea of setting theta based on some kind of feedback loop, then you need a PID controller on that to actually set theta. Does that make sense?
Yeah, well, it's,
Oh,
I mean, but basically to me, it seems like you got you got a choice. You got a heading, you got an absolute heading loop, or you got a heading velocity loop. So you either want an absolute heading to go in a specific degrees, or you want a heading velocity and you want to keep the velocity at 0, or if you want to turn, you want to change the velocity to something.
Right.
if this you have an estimation of your position and you want to use that position to go somewhere, right?
Or just to maintain the current heading, I think.
I just want to make the robot, it's a mecanum wheel, and because of the way the wheels are different weight on the different wheels, it's not predictable on motor velocity versus robot direction on the floor. So I just want to be able to turn in a certain direction and have it hold that direction no matter how the thing translates.
So I wonder, your estimation of your direction can be anyway. It can be any source from another
Right.
instrument
That doesn't
or
have
from
to be
your odometry.
doesn't have
But
to be a
I think
compass.
it should decouple, like it should decouple from how you estimate from how you use it. That's, I mean, I guess that's what I think makes sense. You can figure out how you make the estimation better without worrying about affecting the usage of that position information or the heading information. So does it make sense?
I'm not quite sure I followed you.
I mean, say you're using information from stored somewhere. So something else updated, but you don't really know. But yeah, just use it, and then later figure out, okay, I'm gonna use one way to update it or another way to update it. But that's kind of separate from how you use that position information. I think that's decoupling. Yeah.
Carl, you showed us a week or two ago your mecanum robot doing various exercises, and one of the exercises you were trying to draw a circle, drive in a circle and
Right.
maintain a constant heading, but it was actually kind of oblong. Turned
Yes.
out to be an O. Is that the problem you're trying to solve here?
There was two problems in the oblong. So the fact that it was oblong is one problem, but I think the other problem was that as it went around the circle, it tended to rotate a little bit. So what I was wanting to do is, before I solve the oblong problem, I wanted to keep it to where, as it would translate, it would always keep pointing in the same direction. So whether it's translating in a circle or whether it's going as a diagonal, because I can't trust the motor velocity to have a direct correlation to the positional or the directional velocity, I was trying to figure out, if I just want to have it drive in a straight line, whether it's a diagonal or whatever, am I better off trying to close a heading position loop to where I always keep it at the same heading, or am I better off to close a heading velocity loop where I say, whatever the forward velocity is, make sure that the rotational velocity is 0. So it's a velocity loop versus a position loop in my mind. Heading velocity, so change of heading rate, or heading position, always the same heading.
Yeah.
I think I understand what John was asking, then, which is that there's actually two different problems. One of the problems in sensing the proper heading.
Yes.
And the other problem is using that information to control the robot.
Yeah.
Is that right, John? Did I properly paraphrase that? And so whether you use that as a velocity or as a position control, I don't do it. I don't do that either way.
Really?
Yeah, basically what I do is I count on the PID controller to keep the wheels at the requested velocity. And then the gyroscope is involved with odometry, which is a higher level navigation function and doesn't have anything to do with the lower level. In other words, the gyroscope is not fed to the PID controller. It doesn't know anything about that. But at a higher level, there's a calculation going on as to where I am and to where I want to be. And based on that, the navigation uses the gyroscope as part of that. In your particular implementation, you obviously can't use the wheels to derive the direction. That's what you were saying.
Right.
So you use a gyroscope and you integrate that gyroscope and spend some time getting that all trimmed out and everything, and then it will give you integration of that gyroscope. Those array gyros gives you the heading that you want. Then the other piece of odometry is that once you have that heading, you calculate from the movement of the wheels. So when your robot is moving forward and backward, you told us that that was very repeatable, but when it's moving diagonally, it's not. So you really can't use the wheels to do that calculation.
Right.
So basically, all you really have is the gyroscope. And unfortunately, I don't see how you drive a circle with just a gyroscope if you don't really know where the wheels are.
Oh yeah. No, it's not. I think the gyroscope's not going to solve the oblong problem. The gyroscope would just it would solve the orientation problem, right? Because my theory is that if some of the wheels are, for whatever reason, having more traction or something, that's causing it to kind of like rotate as it traverses around. The one thought I had was that, well, if we can at least keep it in the same orientation, then maybe it'll cancel out. Because if it's a little more oblong one way, it'll be a little it'll undo that on the way back.
Well, you can surely use the gyroscope to drive in a straight line. You're assuming that the gyroscope is always giving you the same heading. Let's assume a perfect gyroscope, no drift. So it's just an angle.
Yeah.
It's separate and distinct from the direction that your robot is pointing. So to drive in a straight line in any direction is simply to keep the same offset between that angle and whatever way you want to go. And you can put that in your steering loop. So that, and I guess as you're describing it, that would be a velocity.
Heading velocity, because it would want to keep the.
I want to keep that number 0 when I subtract the direction I'm going from this fixed gyro reference I have.
So just to clarify, so as Carl mentioned and David, I think, clarified as well, you wouldn't put the gyroscope on the PID controllers that are controlling the motors, but if you have a PID controller that's controlling theta for steering, a third PID controller, in other words, you're not doing a left-right power on the PID controllers, you're actually doing a velocity and theta, as David has talked about. Then if you say, okay, the robot is now set on a certain heading, and we're not talking compass heading, we're just talking a heading, that if you have a PID controller for the theta of steering, then whatever that particular heading is, we'll say it's 300. You say, I'm going to drive at 300, whatever that is, not a compass heading. And now if it starts to alter from that particular heading, the gyroscope will give you a positive or negative feedback loop into the steering PID controller and help you stay aligned. Does that sound like a good summary?
Yeah.
I got to turn myself on. The only caveat I would add is that you don't really need a PID controller at that level. All you really have to do is request a turn in the direction of the error. And you probably, for navigation, you probably helpful to have a little dead zone in the middle. So if the error is small, you're not swimming.
Well, that is a PID controller with only P. And that is what we do. We use a PID controller for steering.
I don't think that's the case, because what I'm saying is that you turn a same fixed amount. If the error is to the left, you turn left a fixed amount.
Oh.
Now, if you're doing this by If you're doing this by a continuous message paradigm, which is what I'm doing and what Murray's doing, I'm not sure what Carl's doing, then you're sending updates. You're sending updates to the motor all the time. In my RCAT robot, that happens 25 times a second. So 25 times a second, I test and I say, well, I need to turn right. So I issue a right command, but just for that 25th of a second. And the next time around, you test again. So the amount of turn is not proportional to the amount of error. And so in that sense, it's not a PID control.
I have a question for Carl. How many PID loops do you have? Is this one per wheel or is this one for all wheels?
Well, it's you know, the gyros, the IMU is not yet connected to the robot. So the the robot platform at the moment has one PID loop for each of the 4 Mecanum wheels.
Okay.
So when I want to go forward, you know, I have a abstraction layer between the controls on the you know, this guy. I have an abstraction layer between this and the 4 wheels. And the abstraction layer says forward, left, right, or turn. So it takes those 3 commands and it maps them together and says, well, if you want it diagonal translation and then turning at the same time, then what it'll do is turn that into 4 separate velocity commands, one for each motor. So what I would do then is take the IMU, all right, and I would mix it in with the command for the rotation control. So in my mind's eye, I'd have one of these buttons. I'd say heading, lock heading. Basically, I'd say lock heading, and whatever the current heading is, I mean, it doesn't matter which way it's aiming with respect to the real world. If I push the lock heading button, then it'll turn on the PID loop. I was imagining a PID loop. It could be a fixed per sample response like Dave is describing, but I was imagining a slower PID loop compared to the velocity loops on the motor, so that I'd hit lock heading, and then no matter how I translated it, the gyro loop outside of the motor velocity loops, the gyro loop would tend to keep it always aimed at whatever the heading happened to be when I pushed the lock heading button. And then with that trick, see, I could even like if I have lock heading selected, and if I have these all the controls live at the same time, if the PID loop is on to hold the same heading, I should be able to throw disturbances in with my joystick, and the PID loop should take them out.
You know, one other cool thing about using the gyro for the heading is that you can pick the robot up off the ground, rotate it 90 degrees, and set it back down, and it'll rotate back around to where it should have been. Which you can't do with this wheel odometry. Won't do that because when you pick it up off the floor, it's lost. But with the gyroscope, it will. And so that translates into thousands of bumps and, you know, scrapes and things that might shove the robot all get removed because the gyroscope knows that it happened, whereas the wheels didn't.
And that's what I was thinking, that's why I was thinking of the PID loop, because I figured I could make a tighter and faster response than the fixed error correction per sample rate approach. So I was thinking that to dial in the PID loop, I would basically have a routine that you know, in software I just push a button to watch it, and the button would it would give it a step response, and the robot would have to and then it would turn on the PID loop and say to try and correct it, and I could see if it overshoots or not. And then so I figured I could just very quickly tune it in that way.
The only part I don't understand of that is when you say I'll turn on the PID loop, why isn't it on all the time? And you just steer through that.
Well, yeah, so I guess it depends on where you mix. Like if I would mix, it depends on if I want to mix this control in as a top level reference, or if I want to mix it in parallel with the gyro feedback. And my thinking is to mix it in where this adds with the gyro level feedback, because then I can perturb it, and I can watch the PID loop response to test perturbations, right?
So when you say turn on the PID loop, that as I understand it, you mean lock its heading.
Yes. Yeah. So like, let's say the heading is, let's say it's the robot's steady, and I click the lock heading button. Then if I would, actually it's a little different. So if I would say lock heading, then let's see, then it would okay, that would require a position loop. Then I was gonna lock the heading, turn off the PID loop so I could turn the robot, then turn the PID loop back on, and it would want to snap back to the original heading. But that doesn't work with the gyro. That only works with the position loop, doesn't it? Okay.
Sounds
Yeah,
like the lock heading is
I'm kind of with David on this one. My thought had been to just have a pit, because it's also with the conversation with Doug as well, is that I just have kind of planned that once I've got to the point where I've altered my robot from being a left-right power to velocity and theta, which is like a next step up. Once I've got theta as a variable in my operating system, I was going to put a PID loop on that, and that's how I was going to do my steering. And then this idea of locking and all that would just be another level on top of that.
Yeah, it sounds like a mode of motion. It's like how you use that theta to drive your each wheel's PID loop, like the reference.
Yeah, as David said, it's just one level up, I guess.
Yeah.
Yeah. And
Carl, I like your process for wanting to use a joystick to perturb the situation. We use a slightly lower tech approach. We go over and kick the robot.
See, that's why the robot overlords are going to kill you first. See,
that's true.
That's what
Yes.
John Spindle said, that it's unfortunate there's no way to do an impulse response to our robot. And I thought, I got one right here at the end of my leg.
You do realize it's a robot form of karma, that you keep doing this. Eventually, like I said, 10 years from now, there is going to be a robot that's going to show up in your bedroom door, open, and just do something nasty.
It's gonna kick me. Yeah.
Like, cut it out and then do something very heinous. Yes.
I do have a comment about, I wish John was here. John doesn't join these, I think. But about his observations about tuning PID controllers, and having Kareem here would be useful because he has probably more experience in this than anybody. But my observation over the years has been that there's not really one correct way to tune a PID controller. It depends entirely on what you're trying to do. So, for example, if you tighten up the parameters so that the motion is really tight and robotic, if you will, or you can loosen them up so that the things tend to flow into each other, and that has a lot to do with what you're trying to accomplish and also with your aesthetic as a robot builder. The other example I would use in the balancing robot, which it's a little more complicated because there's two proportional errors, the tilt and the wheels. But basically in that, if you tighten up the PID controller, then the robot will really resist being pushed. It'll be really tight and hard to move. You can loosen it up so that if you give it a little push, it floats away from you like a puck on ice, and floats across the room and bounces across off the far wall and comes back to you. So again, it depends on what you're trying to do. The idea that there's one right set of numbers that can be derived from some process and that's the correct solution for a PID controller, I would take exception to that. So I think I saw you nodding, Kareem.
No, I completely agree. That completely tracks with our experience. It's always application specific.
Well, just think about elevators. I mean, there's a PID controller on an elevator, and you certainly don't want that one to be too harsh.
No.
Plus, when you
high G acceleration or deceleration.
Also, when you tighten up the control like that, it really you're continuously driving your output. So you really got to take a look at the duty rating of whatever you're driving.
The power.
Yep.
Yeah, tight loops are tough on batteries.
Yep. And loads.
Well, that's a good point. You know, the electric motors we use and these lithium-ion batteries are so powerful, you can easily just strip the gears off. That little spur gear will act like a router head and grind off the teeth on the big gears. It's very possible to do that.
Cool. All right. Well, thanks for the feedback. I'm guessing that the basic answer is it's easy. It depends. Love it.
Well, Carl, so I think I got the idea, the gist of what you were trying to do in terms of fix the heading and you have a wonky wheel or something like that, that on the way back, it would sort of unwind the same in the same way. I'm not so sure with Mecanum that it'll really behave that way. And we've discovered that if you're trying to do anything really precise, with Mecanums, it's almost always better to drive like you normally drive and actually rotate the robot in the direction that you want to drive. It will always be more accurate. The only reason to strafe, those sideways movements is when you're in a tricky situation and it really helps to shift sideways. But for the most part, it's always going to go faster, more reliably, more efficiently when you're driving it sort of, just like you would a regular differential steer robot.
So I can accept that from the functional point of view, but back to the
it's
aesthetics.
A practical point of view, not an aesthetic thing. Yeah.
Well, practical is functional to me. Yes. So if it's good on the aesthetics view, so I'm not yielding just yet. It seems to me that given the issues with the magnetic compass that we all know about, it seems to me that where I'm probably going to wind up in Carl time, days or years from now, more like years, decades, I don't know. It'll be a combination of gyroscope for rate, like a rate gyro, and optical flow for position on Mecanum. That seems to be where I'm aiming.
Well, Carl, there was another thing that occurred to me, and it kind of comes back from that video that David did years ago. He pointed out that robots and humans have certain things in common typically, and that is we have all our sensors on the front of our body for the most part, eyes and ears and things. And that unless you want to put all those sensors all the way around your robot, then sensing in the front of your robot, like on my robot, almost all my sensors are on the front. So if I'm going sideways, I don't know if I'm going to hit something. I don't have any bumper sensors. I've got nothing. So I have to say that, as Kareem said, I want to turn my robot in the direction it's going because I'm not going to sense if I run into something.
That's so practical. That's so practical.
No, I live on the edge like you, right?
In other words, boring.
No. I'll just add sensors to all four sides. I mean, why shouldn't it cost 4 times as much in sensors and power and CPU and batteries and everything?
Hey, like the government. Why build one of those things when you can build 2 of them for like 4 times the price? Awesome.
Why not? Okay.
I will say every time we've had any kind of public showing and somebody shows up with a robot with Mecanum wheels and people watch it moving sideways and diagonally, they are always gasp and oohs and ahs.
Yeah,
the cool factor is definitely there.
Yeah, that's why when I'm doing my 3D printer showing off and talks and everything, I don't take my Cartesian, I take my Delta. One, it travels a little better, and it's far more interesting to watch it doing its thing than just watching a standard, X, Y, and Z thing happen to make all this stuff happen. It's just far more interesting to watch.
All right, so bottom line is don't associate the word practical and Carl in the same sentence because it's a bad idea.
We weren't, Carl. We weren't.
Okay, good. All right, so who's next? Any more impractical things to discuss?
Well, since we were talking PID loops, I'll just have a quick update. As many of you have been knowing, I've been talking about this new robot, which is the KD01, which is the smaller differential robot that is the version of my bigger robot, but it has the same front bumper, uses a smaller 12-volt version of the Makita battery and a Raspberry Pi, and pretty much kind of the same drive and everything. Now, I've been trying to run this thing in a little rotate in place loop, and that was the discussion that we were having on the mailing list. And it turns out that I think the problem has nothing to do with hardware. And it looks to be the same problem I was having with my PID controller before, which was if I came to a stop, the robot's wheels would sometimes kind of just jitter back and forth. And this is something we've talked about for several months. And finally, because of this particular test, I've located the problem. And I think it has entirely to do with a lack of hysteresis in the PID controller at 0. So that means when it gets around 0, the PID controller is still feeding small numbers back and forth, which are being added to the power loop. And so the motor eventually kind of goes, oh, I've got something to do. And then it jerks a little bit. And then the PID controller reacts to that. And you just get this back and forth kind of little jitter motion on the wheel. And I think the solution, actually, I'm kind of wanting to ask either David or Kareem, is it just to put a little bit of a hysteresis on there in the Python that says if the set point of the PID loop is 0 and I'm still getting numbers out of the PID controller, anything below or above a certain value, maybe I should just 0 it.
If the set point is 0 and the encoders are returning 0, that is, you're not really moving, then that's the problem. So how are you collecting your encoder count? Why aren't they 0 when you're sitting at 0?
I am not sure of that, and I literally just as we were starting this call was looking at this thing running and seeing realizing the PID controller even at 0 is still sending back small values. So there's something, and I'm even resetting all my state variables in the PID controller when I get to 0. So there's something mysterious going on, but at least I'm now looking right at where the problem is. So it'll be something like that.
Is it oscillating?
Your code is too complex, Murray. Time to start over.
Thanks, Chris. It frankly could be oscillating, but it looks like it's just coming back and sending little values. Yeah, maybe doing something like this. It could possibly be. Yeah. I haven't graphed it.
I wonder if you got noise on the feedback line, maybe.
No.
Can you log the input
This is
to your
using
feedback?
all effect encoders. But
Is there a way
something
you log the feedback?
Did you twist the wires?
No, I think this is not a hardware problem at all. This is entirely software. The robot is at rest. I've zeroed out all the state variables in the PID controller, and the PID controller, which is my own code, by the way, is still sending 0.45, minus 0.45, minus 0.8. It's sending values in, and then that's accumulating until the motor finally jerks a little bit and then reacts to that. And it kind of gets into this thing where the motors will just kind of go back and forth because of this.
Is there a way to turn your motors off when it's, close to or in that hysteresis band?
Well, that's what I'm saying is I don't have any hysteresis, and that occurs to me that one solution to this would be to solve the problem from the PID controller, which is what I think I should do. The other one would be to put hysteresis and say, if it's set to 0 and there's still numbers coming in within a certain threshold, just 0 everything. But that's kind of cheating, it seems like.
Maybe turn it off when it's small error, like just turn it off. I mean, yeah, does it make sense when it's close to your target?
Well, that's the mystery, is that why is the PID controller still sending back small numbers? Because the motors aren't turning, and the encoders theoretically shouldn't be sending anything.
If you
Murray,
hide
you
the
remember
problem instead of fixing the problem, eventually it's going to come back and bite you.
when you showed us your first video of the robot spinning in place? By the way, the second one looks great. You showed the first one. It seemed like that the motors were speeding up and slowing down. So as if there was some small oscillation, the same oscillation perhaps that you're seeing at 0.
I will correct you, not because you're wrong, but because I was wrong. That first video was actually running code that had kind of an error in it. It wasn't actually ramping up the acceleration up to full speed that was happening in that first video, which is still online, wasn't happening because I was actually ramping the speed up. I actually was setting, it was a mistake. I was setting the PID controller to full speed, and it was actually slewing up as fast as it could. And then it decelerated. So it was entirely an error. The second video actually has it going up properly, cruising and then slowing down. So it was actually a code error in the first video. I'm not sure, I could try to evaluate it, but I'm not sure it's worth it because the second video shows that I finally got the code right.
I have another observation that this goes back to Carl, if I can be so abrupt, that Murray had some experience. Is Ray here? Yeah, with the B&O 055. And Ray had said, oh, you have to turn off the magnetometer. You have to turn off the compass to use it indoors. And that was kind of our accepted wisdom. I ran across a thread from people from another robot club, and they were talking about basically that the full fusion function doesn't work. That is, that they also had to turn off the magnetometer even using it outdoors because there's something wrong with that code. And there was a discussion about why that was the case. I've got one of those, but I haven't really done anything with it. But there appear to be two modes there. The web that's called 9 degrees of freedom, and one that's called fusion. And I think the fusion one doesn't use the magnetometer, and it's the one that everybody seems to be able to get to work. But there may be something more generically wrong than just being indoors with that IMU.
Well, I'm not. Is that a question for Carl or for me? Oh, David, you're muted.
It was really a question for Ray.
Oh.
For Ray. Hi, Ray. Well, I don't know. I think that was kind of my experience with, can soccer. I, tried to use the magnetometer to basically get it to point back to where it started from, in the opposing goal, and just couldn't get it to work. And basically, when I used the gyro, it worked fine. So, by itself. But I don't know if that answers your question or not.
Well, I think everybody's experience on that seems to be the same. My only observation was that previously we thought the reason was because it was being done indoors. And now I'm seeing people say, no, it doesn't work.
It's this fusion mode versus the 9-DOF mode. Thank you. That's a very good. That sounds like that could save some hair loss at the future here. That's
I've just brought up the documentation I have in my Python code implementing the BNO 55, and I copied the documentation, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 modes on this thing. And of them, 3 of them, the compass mode, the end-off FMC off mode, and the end-off mode, 9 degree of freedom mode. So there's 3 modes that use the magnetometer, the rest don't. And my experience is that when the magnetometer is on and I do that shake in the air thing to get it to calibrate, once it's calibrated, I was getting extremely good accuracy on the compass heading, on the absolute compass heading, until it lost calibration. And so I would put it on my bench, and I've got that little turntable, and I could sit there and aim the robot, and it would follow compass heading 0 to 360 degrees very, very accurately indoors in my study with all this computer stuff around it. And it was great until I started driving the robot around, and then invariably in a few minutes it would lose calibration and then tried to get it back again. But when calibrated, it's great. It's just that it loses calibration, and there's that whole black art of calibrating that Bosch have got in that chip that makes it impossible to know how it calibrates or to help it calibrate, apart from picking your robot up and shaking it around. So, but I'm kind of leaning towards getting to the gyroscope rather than the absolute compass heading for steering navigation. But I still, as I've said, I still want to put 2 IMUs on a robot and see if I can get both of them to figure a compass heading. And then if they're both agreeing with each other, I'll say for at least now I've got compass heading, but not expect that to be 100% of the time.
Murray, were you looking at when you were reading the data? If I remember from the early scans, it indicated that it would provide the API would give an indication of whether it was in calibration or not, so that like it was whether the data was dirty or not. Were you using that?
Yep. In fact, what I was doing is that it gives you a Boolean for the, no, it's not a Boolean. I think it's a 0 to 4 value or something like that.
0 to 3, I think.
0 to 3, yeah.
Yeah.
On each of the different, accelerometer, compass, gyro, and magnetometer, it gives you a 0 to 3 value on what it thinks its confidence in that sensor is. And what I was doing was, when I got a gyroscope and magnetometer to say it was relatively good. I would then take my what was it? I'd have to look. I've got the code right in front of me. I was taking basically the two outputs. One of them was the quaternion value and comparing it after conversion to quaternion with the what's the other one called? Euler?
Euler.
Yeah.
Euler.
So I was taking the Euler value, converting it to a quaternion, taking the quaternion value from the sensor, and if those two were relatively accurate within 5 degrees, I was saying, okay, the thing's in calibration. So it was kind of like, if this, this, and this, and this, then you can say we're fine. And that's actually my code. If you look on the BNO 55 library the class that I wrote, I think it still does something like that. I haven't looked at it recently, but that was basically, once I picked up my robot and did that, it would then align and turn on, I think I got to a 2 maybe, not a 3 on one of them and a 3 on the other, basically saying those two sensors were calibrated. And then I would take my Euler, convert it to quaternion and a quaternion, and all those together would give me a heading, and that heading was pretty good. That's basically the algorithm I was running.
I still don't get the whole idea of converting your quaternion to Euler or back and forth. I mean, the sensor is giving you, it has a single solution internally, and it'll just give it to you in Euler or quaternion depending on what you want. It's not like it's two different readings.
Measurements.
They seem to be. I'll have to look again. Put it this way, I might be remembering wrong because it's been months since I looked at this, but
I mean, they're just different representations of the same information. It's just
no, I'm not disagreeing.
The Euler has a problem with with a particular orientation. Yeah. Right.
In the current version of the code, it looks like I'm ignoring the Euler. So yeah, it looks like I'm only taking the quaternion value.
The only place the Euler really has a problem is if you go through the zenith.
Yep.
If you go through zero, which is something you would do in a helicopter, or maybe in a submarine, but you're not likely to ever do that in a robot. So you can probably just ignore it. And in that sense, the Euler angles are much easier to use than the quaternion. Really, what you want fundamentally is you want yaw.
Mm-hmm. Well, what I ended up doing is, this was all, believe me, my math skills are, as I was saying to the team earlier, my math skills are from like 20 or 30 years ago. I forgot most of this stuff, but I managed to find a good quaternion library in Python called PyQuaternion, and all I did was just plug my values from the IMU into that, and it gives me this nice value, and I can then get outputs from that.
So you're not reading the Euler angles directly from the IMU, you're calculating those from the quaternion?
No, it looks like I'm speculating, but I think I'm not using the Euler anymore. What it looks like is I'm getting the quaternion value directly from the BNO 55 and using it. It gives you a tuple.
But then you're still probably converting it into regular Euler angles to get a classic heading.
Well, it gives you the tuple of W, X, Y, Z, or Z, sorry. And
I like Z. I'm Canadian.
Are you Canadian? Oh, me too.
From British Columbia.
Oh, okay. I'm taking the tuple and feeding that into this PyQuaternion and getting a quaternion object, and then there's lots of methods off that I can use, and it's just basically a handier way with dealing with the tuple. I guess I could do it myself, but I don't have the math skills. So yeah, that looks like what I'm doing. I basically said if calibrated, then I set a heading value. Otherwise, set a heading to none. So yeah, it looks like that. And the idea being is I've played around with, I think it's like 6 or 7 IMUs now. And the idea is to find an IMU that was relatively dissimilar to the BNO 55. And for that one, I'm using the ICM 20948, this little tiny guy. And I've mounted that up where right next to the BNO 55. And what I'm going to do is try to see if I can get a fusion of the two of those IMUs. That's still the idea. But I know
which version of BNO are you using?
Which one? Oh, I've got both of them. I've got the BNO 55 and the 85, and I think I've said before that I've had very little luck with the 85. The
Yep.
55 goes out of calibration, but I can't make the 85 work.
Yeah, the reason I asked is I was looking up on the internet while y'all were talking, and a lot of different people make those BNO 55s. Is it Adafruits that you're using?
Oh, it
Or-
doesn't matter. The actual chip is made by Bosch, and these are just
Right.
carrier boards. The chip itself is tiny. It's like 3 millimeters square, and they just put it on a carrier board. So Adafruit's only putting a carrier board together. They're
Yeah,
not
they're
making.
saying that they're simplifying using the data because they're doing some of the math inside for you. I didn't know if their
No.
math was wrong.
No, the only thing that the only difference, there's a whole bunch of probably at least a dozen companies making BNO 55 carrier boards, Adafruit, Pimoroni, etc. The 85 difference to the 55 is that there's this extra library. So Kingsbury, or somebody remember the name of this extra library? I
I
can look it
remember
up.
what it is. Yeah.
There's an additional library that gives you, I think, some filtering or something like that the BNO 85 has on it. And I don't think that's on every 85 board, but the Adafruit one, it certainly is. And that's supposed to be really, really great. I don't know why. But the problem I was having is that the thing basically core dumps all the time. Basically, every 3 or 4 seconds, it just core dumps stuff onto the screen, like bin hex stuff onto the screen. And I was in conversation over email with one of the engineers at Adafruit, and turns out that the sample file that they provide does that. So it's not like I did anything. I'm just running their sample file, and every few seconds it goes and spits some stuff to the screen on the console. And so I'm happy to have anybody on the DPRG list have some success with the BNO 85, but I can't seem to get it to work very well. And I'm hardly the IMU expert. I don't claim that, but I'm going to stick with this little ICM 20948, this one. Or the other one that I've been working on is the one that's on the new robot, which is a FXOS 8700 plus an FXAS 21002. I mean, my God, a whole box of these bloody things. It's just amazing how complicated it is to use them.
Turn them all on at once, and you'll never know what direction is north.
Exactly. Anyway, that's it for me. That's the model I'm in. I'm still PID tuning, and then I'll get to the gyroscope. So.
Nice.
And thanks for everyone's help, particularly David. We've been kind of having it on. He's thrown the gauntlet down on his ability for his robot to go over a bump on the carpet. So I've got to do that now.
All right, who's next? Who's going to step up to the carpet bump challenge?
Well, my plan for my robot with the carpet bump, since it cannot do it going forward, is I'm going to make a behavior that turns it around and it can back over it.
Nice.
Sort of like an old Model T. It can go up hills backwards, but not forwards.
Actually, I mentioned in the mailing list, I think this carpet bump challenge might not be a bad thing for the club, to actually have a big thick carpet on half of you put a line down the middle of a plywood sheet, put carpet on one half, and show that your robot can make it to the other side how accurately. It's a good test.
Sort of like the ice cream sticks on the challenge course.
Mm-hmm.
Except with shag carpet from the 70s.
Yeah.
bright red like we had in Des Moines, Iowa.
So who can find shag carpet from the 70s? Hasn't remodeled lately.
There's this rug shop here in Pittsburgh near my parents' home, and I kid you not, they and since it was here 30 years ago or whenever I was growing up, they pull out this VW beetle bug that's layered in carpet. So it's a VW beetle bug. It sits outside with shag carpeting. It's hilarious.
On the outside?
On the outside. I don't know how many times it's been resurfaced, but it's a beetle bug with shag carpeting on the outside.
Yeah. First house that I bought back in the 90s had shag carpet nailed down to, when we peeled it up, was a beautiful red oak hardwood floor. Who would do such a thing? They thought they'd modernize it, shag carpet.
People with hardwood and linoleum, they want carpets. People with carpets, they want hard floors.
Except Chris, he wants one painted flat black.
I did have a link I was going to put in. I intended to put in for Jean last week, and I didn't, so I put it on the mailing list. But I don't know. Do you get the mailing list? Are you on the DPRG mailing list?
I am. I'm not sure which one you are referring to.
I put in a link. Well, I can put it here in the chat. You had asked about calibrating your encoders, and I had a little paper on that.
Yes.
So, if you hadn't seen that, I'll stick it in the chat if I can.
Yeah.
Is there a way to access the chat after the call's over?
You're
We've been recording
right away.
Yeah, we copy paste right now, but we also have been. I think Doug's been posting them up in the website with the recording of the video.
Right, I've seen that.
Sean, I just put the link in the chat.
Thanks, David. I'm taking a look at it.
So how does that work? If you want to look at a link that was posted late in the video, do you have to fast forward to that point, or?
No, the text of the chat is in a separate file. It's just a text file.
Okay.
On the website.
Yeah.
And if you have trouble finding it, just let us know. We'll dig it out. I think I have copies of all of them.
Can anybody hear me?
Yes.
No, we can't hear you at all.
Okay. The reason I ask is because I'm doing this totally on a Raspberry Pi tonight. So it's different. If anybody can I go ahead?
Yes.
Jump in.
Okay. I made some progress on my robot that I was supporting on both sides. I now got a base. So this one's coming along pretty nice. It really does make the wheels nice, being supported on both sides. No rocky back and forth anymore. And I'm setting this guy up, and I'm hoping to do a tutorial on PIDs later on in the month. So that's what this guy, he's going to be the test bed. He's just straight vanilla.
So on the ASSO, how do you connect the ASSO? I'm curious about that. So show it closer to the camera. I'm like, because those are those relatively cheap. So you just ran. Okay, so you connected. Right.
I talked about it before. There's a brass rod. There's a bearing in the bearing block, and on the side that on these particular motors with the encoders,
right,
they have a thread in the end so that you thread the wheel on.
Ah, okay, so you thread it.
That in, and it just works really nice with those. These motors are the $7.50.
Right, I have a couple of them. That's why I'm like going, how do you thread it?
It works really well. So
that means you can put more weight on it effectively. So
well, I'm not worried about that. I'm just trying to get away from direct drive motors.
right.
It's direct drive, but it's supported at least on both sides of the. There's two bearings instead of just one. So this was an experiment. So it went pretty good. I'm pretty pleased with it, and like I say, I've pretty much got the wiring for the motors and the encoders already, and I'm working on the code now. So this should be. I want to set it up so to kind of like show a way, not the way, that you can get navigation out of your computer, out of your robot.
Yeah, imagine these guys don't even have a bushing. There's just the axle rubs on the case.
Yeah, I know what you mean. That's what I'm thinking that the $7.50 ones might have a piece of a Delron or a Teflon or something, but it isn't much, whatever it is.
Yeah. Yeah.
Yeah, it's pretty grim.
Just gets sloppier and sloppier with age.
Yeah. So that's what I was trying to see if I could fix that. Anyway, so that was one thing. And yeah, Carl, one of the things I was thinking about for your situation, he's gone, was that he used a caster wheel, you know, a free floating caster wheel in the center or anywhere in his under, but probably best place would be in the center of his robot, so that he could put a disc on it so that he would know when the caster wheel rotated with his direction, he would know which way he was going.
Good
All
idea.
right. And that, you understand that, Carl? I know you were gone, so I don't know if you caught that.
Basically, he's thinking tracking ball.
I think I missed all of it. I just
Okay.
did.
heard. Did you catch that, Carl?
Probably in the center of your robot, you could put a caster wheel. It's not driven or anything.
Oh, yeah.
It also would detect the direction. You could just put a disc at the top of it, and you could catch the direction that your robot was traveling, and that could
Yeah.
give you feedback.
I think Kareem has mentioned Iron Rain has done that technique
Yeah,
before.
I know they've done things like that. Somebody else in the club did one a long while back, but I was thinking Will did something like that once. And anyway, it's an idea. It just
My experience has been that it's very hard to tell direction from a caster wheel because it can rotate either way, and it's difficult to know directions of road.
In his case, he's going to have his gyro to keep his base in the same direction. His gyro will keep, but he can't tell whether he's going this or like this or like this, because as long as his base is oriented the right way, he's not getting any signal. So he needs something to tell him that he's doing this or he's doing this. You know, for a differential robot, you know it's going in the same direction because the wheels are driving it forward. Okay, you might be turning, but it's the base isn't changing from the wheels. But in his case, the base is independent of the wheels. The wheels could be going this way or this way or this way or this way, and the base could be perfectly saying I'm aligned. I haven't shifted. Now, so
I understand the problem he's trying to solve. I'm just saying I don't think a caster wheel will necessarily give you that information. I tried this once some time ago. Caster wheel just on the back end, and trying to relate what the caster wheel is doing to what the robot is doing. It turns out to be very difficult.
Yeah,
You want to use two omni wheels pointed in different directions.
Okay, that's good.
That's what you want to do, and then you want to make sure that there's some sort of elastic down pressure to keep them in contact with the surface.
Yeah,
right. So you got encoders on those. Those are non-driven wheels. So even if your mechanisms are doing something strange, you're probably going to get good information about how your position is changing.
Yeah.
Yeah, the caster wheel could show you the direction the robot body is moving, but it wouldn't tell you which direction it was pointing. So it could still be drifting, and the caster wheel would still be pointing at the same location, adverse to the body.
But the orthogonal omni wheels would let you take care of that.
Yeah.
The orthogonal omni wheels would measure in both dimensions, and as would a good optical flow sensor, which doesn't require friction; it just requires contrast.
Yeah.
Well, and as Kareem and I have been in communication with Pimoroni, that little optical flow sensor that they use, which uses a drone sensor on their carrier board, we've been in communication, and it seems like they are in the process of trying to acquire the actual sensors from the original manufacturer, the OEMs. And so they're actually in the process of going to build that if they can get the chips.
Yeah.
And the replacement chips are ones designed for working at a floor kind of distance rather than, meters in the air.
Right.
And if they put those out, they might put them out sometime this year. And definitely I'll be buying one because, if they can run like, a couple inches off the floor, and in my tests, that would be perfect. Yeah, and I don't even know if you need two of them. I think just one of them plus a gyro and you'd be fine.
It could
It
be.
seemed like a single one of them would do the trick.
Yeah.
Because they're basically got cameras in them, right? And they're they got many pixels to work with, and they can detect rotation from the optical flow.
So,
yeah, pretty cool.
And the other approach, which no one's mentioned, but it's in the back of my mind, and that is to have some external reference. So, just as Ron Grant showed with his VR setup the one time, where they have 3 tripods in the room, and as long as your object is moving within that space, your object is able to have communication with the 3 different posts, and it's able to position itself in the 3D volume actually. So that's another approach entirely. So something like that, or maybe having a camera facing on the robot that tells the robot where it is, what its orientation is. I don't know. For now, I'm starting with the gyro. 4 wires. It just takes 4 wires and duct tape and a little bit of code. All right. So anybody have some cool projects they're setting up to do on the next week? Major progress next Tuesday? What do we have?
Well, I don't know if it'll be major progress by next Tuesday, but I've been working on this guy with the challenge line following course. I'm going to look at the DOE stuff because I realize that in comparison to the RAMI platform, that the original position of the camera was further back and it's about an inch lower, and just moving it closer to where it was on the RAMI platform, it works much better. So, that's one of the variables that maybe I could play with is, okay, position forward or back of the camera, the height of the camera, because it all ties into, how fast you can turn and track a line without drifting off somewhere. So,
are you running image, analyzing the image at real time on the camera, the full image analysis?
It's a reduced. It's down to 40 by 30 is what the image on the from this camera is. It's like quarter BVs, which is 40 by 30, and then I look at selected pixels and try to determine where I think the line is. And before I do any of that, I do like an edge transform on the image because that gets rid of any issues with a black line, white background, or vice versa, and you can easily transition into the two, and you still see where the transitions are.
Are you moving while taking image or stop and take image?
No, it's moving. It's doing about okay, I think let me see, 5, 10, 15, 20. It's doing about a frame every 50 milliseconds. So it's not that fast, but I do a lot of looking at the values of pixels and setting pixels, which apparently is one of the slowest things you can do in kind of like OpenCV routines. So it takes the most amount of time, but I have to look at individual pixels to make that work. If I switch to the global shutter camera, it's probably at least 3 times as fast. So my frame rate would be much faster.
This is a line scan. You're talking about this is a line scan camera?
It's this one is, I forget what the other one's called. Not a global shutter. I forget what it's called. I guess it's like a moving shutter because the one
No, I think,
scans, the other one.
yeah, right. Line scan. I think line scan should stop and stop and take a picture. Otherwise, there's some.
Yeah, you get some image artifacts with things moving, but it's fast enough that that doesn't seem to affect it because I'm really looking at a thin line of pixels, and so if there's image shift or later in the image, it doesn't really matter that much. So, and it's kind of a semicircle. One of the things I found is if I just have individual pixels, the lines can actually be between where the pixels are and not tell me that it's actually crossed that line of pixels that I'm looking at. So I had to like kind of fatten up the line and include pixels so that if the line was added in like a diagonal to the line that I was looking at, it would still cross one of those. Otherwise, you can get, if you have kind of a pixel here and a pixel here, you could have a line that crosses between them diagonally and doesn't hit either pixel. So because they're single pixels. But I can, if you want to see it, I hooked it up before and showed you what the image looks like.
Okay, wouldn't it be like across like a step, like going for a profile and figure out where the transition is? Well, you already have this edge detection.
Yeah, it does. Yeah, it's just it does like an edge transform over the whole image, and so
Using like just like a half transform or something to detect the straight lines?
no, I'm not using that at all. The only transformation that I do is an edge transform, and the rest of it's looking at individual pixels. I can hook this thing up here. Might take a second.
This blob detection, figuring out these the patterns in there. Maybe add some thresholding to reject the stains. I'm thinking you could get the lines or the bulk shapes in the image. But yeah, well, yeah, that's something to work on when I get this line following.
Okay. I'm going to see if I can do it here. Okay. Let's see if I can do that. Can you guys see that?
Yes.
Yeah. Anyway, so it's just looking at the desk now. It's not rotating, and I've got a bunch of cables and stuff in front of it. So that's kind of the gray pixels are the pixels that I'm looking at, and I actually have a black ribbon that I can move around, and where the two intersect, I actually get terminal. the count is the number of intersections that I actually get. And right now this is, let me see if I can, yeah, there we go. I got too much junk on the desk, that's what it is. So if I move that cable around, or the ribbon around, you can kind of see where it's intersecting that line. And then this cross over here, right here, is the actual X value, or the value that I use for steering, to say where those are actually crossing at. Yeah. So if I move from one side to the other, you know, the X value, so that's like crossing that line, if that makes sense to you. But
You are figuring out this. There's the gray line fixed, and then there's this ribbon where you detected.
yes, so the gray line is the pixels that I'm actually looking at. And when I throw this ribbon down, and it's a black ribbon on like a white desk surface, and if I get any intersections of the two, then like the center is, let's see if I can get it right in the center.
The intersection. Okay.
Yeah. So that's right about in the center of the field of view of the camera, and this is to the, you know, the far right side, and way over there is to the far left side.
So that ribbon is the line to follow, basically.
Yeah. So pretty much the, you know, when it curves around, this is going to be moving back and forth, and that X value down here is an indication of where I think where that line is crossing. So
It's like you have a line sensor, although you have a full image, but you make it as a line sensor, like a you know, series of dots. That's good.
yeah, yeah.
That's
So
cool.
and these numbers here are they're actually the index of the array of pixels. So it's like pixel, you know, number 17 or in this list here of pixels.
Yeah. Right.
So
It's really like a direct, similar to the simulator, right? Where Ron had all these shapes of sensors on there. You can put a shape of this gray line in your image. Yeah, that's
yeah,
nice.
yep, yeah, exactly.
Simplify the process. Nice. Yeah, great.
Yeah, and it's going to be faster than this. This is the frames per second here. It's 20, almost 23, kind of in the lower right hand corner. But when you hook it up to the IDE, it is slower. So,
I see. Yeah.
and you know, all of this code is to just try to figure out, you know, what is this X value, you know, independent of, you know, am I crossing, like, you know, let's see if I can do this right here. Say like I have an intersection, like a cross. You know, I still have to figure out where I should go. And this particular scheme, I just average all these crossings here. So there should be, no, it doesn't look like it's hitting right there. Okay, now it is. So I should have at least 6, 1, 2, 3. I've got split in between 6 and 7 pixels that I'm actually crossing on that gray line, and you know, it still should come out around the center, which is I think 28, 29. So it's actually in this particular scheme, it's just doing an average of those 7 values to come out with this value here. That was one of the schemes that I did, and I played around with a bunch of other schemes, but this is the simplest one. Whoops, just banged it. And you know, the other ones are more complicated. I looked at doing kind of a center average, a left side average, a right side average, and then depending on, whether I had something in the center, right or left, I would do different things to, to accommodate like the acute angle and, right angles, left angles, 90-degree angles, and stuff like that. So yeah, it's very, very much like, what you guys did with the simulator.
Yeah, good idea. Simplify it. Yeah.
Anyway, and I think that's, oh, well, yeah, I actually thought that's what Chris was going to get into doing, but maybe not. I don't know.
Well, I was thinking of using TensorFlow, right? So you are more processing the data yourself.
Yeah, definitely. So, and the camera's fast enough. And so I'm kind of back where I was with the Romney platform. I can do everything except the acute angle and the gap with that code. But I'm actually gonna borrow some things from you, Chris, and add another line across the bottom, like you did in the simulation. And instead of averaging all the points, I'm going to try to find the center point between 2 points that are the closest to each other. So, like if I have 6 points, I should have 3 pairs that are close to each other, indicating that I'm seeing 3 lines, like at the cross or something. And then so it doesn't matter, how fat or how skinny the line is, because that width changes. And try to make decisions based on that versus just the total number of points and stuff. So, because I think I can come up with along with what I call the last X value, the most likely place where that should be. So the selection of where to go next, or that X value, should be easier. I hope. Let's hope. So anyway, that's where I'm at. Oh yeah, I don't know if anybody else has experienced the COVID thing. My wife and I got tested. My wife came back positive. I came back negative. So she's quarantining at home. She seems to have mild symptoms, but I'm just getting tired of waiting for that vaccine. I'm ready to pay somebody, on the hey, how much for 2 shots? But anyway, I don't know how you guys are doing with that, but we were kind of surprised. I didn't think either of us had it.
So what type of test did she have? The rapid or the more detailed, whatever the abbreviation is called?
Yeah, we both did the saliva test. It's put
Okay.
into a vial, and
Because the one where they basically poke it up in your nose is the more accurate one. So
yeah, I guess that's supposed to be the most accurate.
it is.
Yeah.
You know what I heard about those things? I heard that test was never actually designed to detect COVID. It was designed to detect something else. It just happens that they're able to detect COVID with the same test, or to do that thing. That's what I heard. I don't know if that's true or not.
Oh,
but
with the
that's what I
saliva
heard.
test?
Yeah.
Yeah. Yeah, I think the saliva test is like if you get a positive result.
Well, you really want to go. If you do the rapid, you want to go back and have a more detailed test. Basically, what it boils down to in that case.
Yeah.
And then depending upon how severe it is, because there was a coworker I taught with that had a brother who had a type thing.
Yep.
And he was positive, but he got over it. It was relatively a mild case for him.
Oh, was it? Yeah, yeah, yeah.
But
Our optometrist apparently got it and quarantined at home with her husband, and her husband never got it. knock on wood, I'm hoping I never get it. So. But so far, it's
Yeah, but I mean, it is contagious, right? Otherwise, it wouldn't be a pandemic.
that's
So
right.
I guess I don't know how you guys,
And the key is its degrees of. I mean, depending upon how good ventilation you have, you know, how far a distance you are. There's so many variables. It's almost
Yeah.
like you need to put it in that chart that Carl said to figure out which variable is the one that you want to maximize your return on. So,
To do a DOE on the
yes.
situation, maybe, or something.
Well, like John was hinting, maybe it was a false positive.
And it
Say
might be, but I wouldn't count on it. Not nowadays, but I would go, yeah, get a more detailed test in a day or two, especially, and then, you know, check the temperature, can you
Yeah,
breathe,
got a pulse oximeter
and your oxygen count seemingly is important too.
yeah. So
Ray, is your wife quarantining from you?
yeah, she's sleeping in a separate bedroom, and we keep at least 6 feet apart at all times, and she
And I would argue that this case you should probably do like Carl did, which is wear a mask around type thing.
yeah.
Because that helps on cutting down the distance. I mean, there was somewhere out there I saw some article that basically claimed that by wearing a mask, you cut down the feet, you know, so that in theory around 3 feet or less
Yeah.
type thing.
We were trying to figure out, who we possibly could have gotten it from, and it's like, the only thing we do now is, go grocery shopping, and that's the pickup. So somebody comes out and puts it in the back of your vehicle, and I was wearing N95 masks because I had a bunch of them for woodworking and stuff, and she was wearing I don't know, kind of these other masks that I didn't think really worked as well, but so we can't really figure out who we might have been in contact with. Who
Was
knows?
she having,
Maybe.
is she having symptoms?
Yeah, she has kind of like a rash in her mouth, and that's apparently one of them. Kind of mild chills and heat flashes kind of thing.
Smell?
Pardon me?
Well, taste, smell, I think was another one of those things that they were
Yeah, she hasn't
pushing.
lost either of those, so I don't know. Hopefully, it's going to stay as mild as it seems to have been, and we won't have to do anything. So
Good luck.
yeah, thanks. I don't know how.
So when you did the test, was it like 2 days, 3 days in? Because there's that part two that's seemingly 5 days in for the more detailed tests. It's the more accurate time frame. So
Well, she, we scheduled the test after, she developed the rash in her mouth, and that's supposed to be, one of the signs, I guess. But, it took a couple days to do that, and
right.
I think she, had the rash for a couple days before because initially she didn't think it was, had anything to do with COVID, and then, we scheduled the test and did that. So, but it's hope nobody else has to experience it. So
Amen.
Good luck
I
with that.
have a question for Chris. Maybe I didn't get in until late here, and maybe you already covered this, but did you make any progress with your line sensor on your floor?
Well, we did cover it. The short answer is the suggestions from last week didn't really help. I tried your angling, I tried the shielding, and I actually also tried PWM to reduce the IR. And everything just kind of changed in value proportionally. And so I was still getting a broad range of readings from the floor. So I went low tech and put this on my floor, black on top of white. So, it's a lot of work to tape this down. It's just pieces of paper, but at least it works.
So the problems went away with that consistent background?
Yeah, because now I'm getting there's no fluctuations here, right? Coming from this area. That was the problem, right? This area off the line was giving me readings all over the place. Now I'm getting not just a solid line, but I'm getting a solid lack of line. And it's now just a matter of tuning the PID so that I don't need to make super tight turns. I'm not doing actual challenge line following, but I want to be able to take smooth turns. And actually that's what I'm doing as we speak. I'm just fiddling with my PID a little bit to make some turns smoothly and at decent speeds, right? Because I want to be able to go at decent speeds and collect some LiDAR data without falling down my stairwell.
I was going to say the stairwell is his biggest problem now. So you may want to do like they do on Rumbles or that, where they had the real infrared light going across areas that you don't want to go into.
You can also just use one of those little gates that they use to keep children from falling down the stairs.
I have a couple because we recently got a dog. Recently, like
there you
3-4 months ago. So I have a couple of those gates up right now, but it's at the bottom of the stairs.
I was going to say, with COVID, there's probably a surplus of really rough toilet paper, and that's probably the right width for, making a little course,
So the bottom line, Chris, is that you do have a repeatable enough test set up that you'll be able to collect the data that you're after.
That's right. It just takes a little bit more work to put it down. It involves a lot of taping of the edges. Otherwise, those paper strips, if you walk over it, they'll be damaged immediately. So that's the problem. It's just a little bit more work than I was hoping. But rather than continue down this rabbit hole of trying to figure this out, I just decided to go low tech.
Bye, guys. See you.
Alrighty.
Yeah, it looks like everyone's leaving. I didn't do much.
Getting late.
But, maybe with this opportunity, I want to maybe ask you guys how my implementation look like for the mechanical odometry. So can you guys see my screen?
Yep.
So basically, Carl, maybe you can tell me if it looks right. I copied it off of a paper. So it's like 4 wheels translates into the X, Y, and rotation change. And the way I made it is, it's like each encoder interrupt, I will get like 1 wheel moving certain distance. So I'm gonna basically update the odometry per encoder interrupt on the particular wheel. So it'll be something like this. If the encoder is increasing, I'm gonna do these bunch of things, updating the X, Y, and theta. If it's decreasing, I'll do the kind of reverse. But yeah, does it look right? Anybody have a? Let me make it larger. Let me see if it makes. Does it make larger? Let me see. Zoom
I think
in.
Shift Plus should do it.
Zoom in. Oh, Shift Plus.
Or you
Yeah.
get it there too.
Yeah. Yeah. So what I'm gonna do is, like, the encoder interrupt will call increase position with which wheel it is on, or increase or decrease. And it'll do these update for X, Y, and theta following these equations. So does it make sense?
I don't know how to calculate X and Y without using a sine and a cosine. And I don't see a sine and a cosine here.
Oh, this is Macadam wheel. This is Macadam wheel. I see what you mean. Yeah, the theta. But yeah, Macadam wheel is like this. But okay, I think, yeah, my main concern is usually I see like, two wheels, all the change from all wheels. Now here's the update of the next position. Now I'm doing it one wheel at a time. I think it should work because it's incremental. It's a little bit each wheel, and each wheel will come in. But I mean, I don't know how do you guys update the odometry? Do you look at it once in a while and update all wheels together, or is this every interrupt update the odometry?
Well, speaking for myself, I updated at the same rate that I read the wheel encoders, which is at 25 hertz. So every 40 milliseconds, I read the wheel encoders and I update the position, the location.
Uh-huh.
Same here.
Yeah, I do 20
And
hertz.
John, if you look at that link that I stuck in the chat earlier,
I saw that. Yeah.
For normal two-wheel odometry, the algorithm is included in there.
Yeah, that's very detailed calibration. And yeah, I'm gonna follow through that to figure out my.
But I'm specifically referring to the first section where it lays out the algorithm.
Yeah. Yeah. I think I updated
That may
fast.
be
It's not bad.
That may be useless with Macadam wheels.
Now I know you guys updated 25 hertz, but let me try this. I think if I updated per interrupt, it wouldn't hurt. It's like I have the exact tracking.
I mean, the thing is that with a nice fixed sample rate, then, I mean, it's easy to divide counts by sample rate, by period, and you get a velocity, right? But here, if you're updating the count on every interrupt, then somehow you have to add the element of fixed time in there, or you have to element how much time has elapsed, unless you're measuring the time between each interrupt.
So look, from this, I'm thinking it doesn't really matter of my speed. It matters where my wheel is. I mean, yes, speed matters, but I mean, basically the whole thing is like a rigid body. So if I know my wheel moved certain distance down and goes somewhere, it's like it's not time related.
Then you're falling prey to what I showed a couple weeks back, where the I basically did those calibration tests, John. And you can see the video, the recording from that meeting, where I moved the Macadam wheel robot a certain distance 10 times front to back. Then I did it diagonally 10 times. I did it sideways 10 times, and I did that on different surfaces. And what it showed was that because of the way the Macadam wheels fundamentally work, and because the weight isn't exactly even on all four every time, and it might even not be coplanar with the floor, it wound up meaning that you really just can't count on trying to back out position from Macadam wheel odometries. You just can't. It just is not going to work.
Yeah.
Or if it does, you're going to spend so much time trying to apply, I don't know how many different fudge factors to try and get there, but
maybe also I should clarify that on the systems that I'm running, the encoder counts are actually counted in hardware by a hardware register. So there's no interrupts that are generated by the encoders. There's just a hardware register, and I can read and zero that register anytime I want. And I read and zero that register 25 times a second at a very precise rate. So it's, as Carl said, the DT you can ignore because it's always the same. If you're sampling, as a matter of fact, as a general rule for robotics, if you can sample everything at constant rates, it simplifies all the math. It simplifies making filters and everything.
Everything.
It gets much simpler if you can ignore the DT because they're equally spaced. So for, at least for this robot I'm describing, every 40 milliseconds it goes and reads the hardware registers that tell it how many encoder counts have accumulated since it was last read, and it zeros those registers so that the accumulation starts over again.
Mm-hmm.
And the encoders themselves are collected in hardware and they don't generate interrupts. I effectively just ignore those.
Mm-hmm.
And in the conversation David and I have been having offline about trying to figure out what's going on with my robot, it turns out that I, as you would expect, was assuming that I had a 50 millisecond loop on my PID controllers, but it turns out that at the moment at which I was getting this surge, I was actually getting that 50 millisecond was actually changing. It went from like down to like 9 or 10 milliseconds, and then it would be 25, and then it finally got back up to 50. So something was going on there, which I have yet to figure out. But I agree with David. I wish I had like a hardware level reliable clock, but on a Raspberry Pi, you're sharing an operating system, so that whole microcontroller, microprocessor, single board computer argument there.
I mean, the clock is pretty damn reliable on the Raspberry Pi. I'm not sure how you're reading it, but I think we've had a similar conversation before. But
believe me, it's my code. I know that. There's something I'm doing wrong. But there is one thing, and that though is that when you're running Python code and you are running it multi-threaded, the threads may not be always getting full time signature allocated to them every single time. I don't know. That seems bizarre to me as well. I would think that even though I think on a Raspberry Pi you've got 4 cores, and I'm running 2 of my PID loops, and they seem, if I look at the stats, it says 0.0501, which is 50 milliseconds, really reliably, until I had this little burp, and then it kind of does this weird thing, which I don't understand it either. Could be Python, could be me, could be something else, don't know. It's kind of a mystery. Anyway. I gotta go. It's 5:30, 5:40 here. You guys are getting late. Half of you should be in bed here. So, you guys next week.
It's almost midnight. We'll see you.
Carl, at some point we talk about this telepresence thing, right?
Yeah, but I don't think tonight, man. I can't.
Yeah, I
can't.
We need to like call a meeting just for that at some point.
Yeah, I was going to say I have 10:41. I don't know what time you all have, but
it's 11:40 here in Pittsburgh. So and Connecticut too, I presume.
So I would say
see you later, guys.
Tuesday.
Catch you next Tuesday.
Okay.
Night.
Bye for now.
Night.